Hi, everyone. We'll start in a couple of minutes. I just wanted to say a little bit about who we are and what this session will be about and so on. So my name is Shravan Hansoge, as you can see. I'm a faculty member. I'm a helioseismologist and a faculty member at the Tata Institute of Fundamental Research. Together with me is a very bright student, Vishal Upendran, who will be co-chairing this session. Vishal, I first met him as a visiting student from IIT Madras. He did a project with me, and then he's now pursuing a PhD on some very exciting topics with Durgesh Tripathi at IUCAA. So we'll be sort of monitoring the time and reading out questions from the chat box to you. Vishal will interrupt you when you have about 3 minutes to go, and remind you that your time is sort of coming up to an end. We have a very exciting session this morning. Very distinguished speakers. Nat will describe various interesting aspects about flares, CMEs, and space weather. We'll hear more about CMEs from Kathiravan. Is his mic working now?
Yeah, he's going to speak from here in the auditorium.
So he has joined us here in the auditorium. Okay, sounds good. And Monica Bobra will be talking about some of her interesting work on flare prediction. And finally, we'll wrap up the session with Anshu Kumari, who will tell us about radio bursts and CMEs. So with that, it is 8:15 dot, and I'd like to invite Nat to please give the opening lecture this morning.
Okay, greetings everybody. I'm going to share my screen.
Nat, I will interrupt you 5 minutes. You have 25 minutes for your talk.
Okay.
I'll interrupt you at 20 minutes. I'll give you a signal there. Then you have 5 minutes. Okay?
All right. Okay, good. Are you able to see my screen?
Yes, we can see your screen.
All right. So this presentation is about flare CMEs and space weather. And I added a tail to my title because some highlights, because there are several thousand papers written on flare CMEs and space weather in the past 2 decades. So it's impossible to talk about everything, but I thought I should give some highlights of current topics and some topics that are of particular interest to me. So I'm sorry if you're disappointed that I'm not giving a very comprehensive lecture. So the question I want to focus is, do all CMEs have flux ropes? And that seems to be the case, at least for those CMEs that arrive at Earth. They all seem to have a flux rope structure. And the flux rope nature of CMEs is inevitable for the sun to get rid of the accumulated helicity in all the magnetic regions. Otherwise, the sun will become a banana. So, and also very recently, there is a very nice paper by Marubashi et al. In 2015, in which they showed that all 1AU CMEs can be fit to flux ropes. I remember Lipping et al., they can fit only a subset of them as flux ropes or magnetic clouds, but Marubashi-san has shown that it is possible to fit flux ropes to all of them. So in this talk, I will focus on flux ropes, and these flux ropes are actually connecting FLAIR, CMEs, and space weather. So I will be talking about a bunch of topics. First one will be hot flux ropes. These hot flux ropes are a hot topic because they were discovered about 10 years ago. And there are a lot of questions about them, whether they are really the flux ropes that come to 1AU or they are some interior part of the real CME flux rope. It's not very clear. And the related question would be, do flux ropes exist before eruption or they are formed during eruption? And the flux ropes, how they are formed, you all know that it is due to magnetic reconnection. And the magnetic reconnection not only produces a flux rope, but also produces the flare that we observe. So that's the connection between flux ropes and flares, or CMEs and flares, via magnetic reconnection. I'll also talk about how reconnection can lead to the observed CME acceleration, which is between 100 meters per second squared to about 10 kilometers per second squared. And how the total reconnected flux is related to the CME and flare properties. And then I will show some estimates of how CME magnetic field is estimated near the sun, which is very important because then you can see how the CME field evolves and becomes, geoeffective later on. And then I'll talk a little bit about the difference between flare and flux rope, because in all the previous topics, I see their connection, but there is some aspects in which you have to treat them as separate structures. And that's related to gamma ray emissions from the sun, which can last for, about half a day to a day beyond the flare. So they are very interesting observations made by Fermi satellite. And the last topic would be how the state of the heliosphere affects space weather consequences of CMEs. Okay, so hot flux ropes were identified by Reeves and Golub in 2011 and further studied by Cheng et al. And there is a recent article by Nindos et al. 2020. And the picture I have on the left-hand side is basically images made by AIA SDO in the 131 angstrom wave band, which is sensitive to 10 million degrees. That means the structures you're seeing here are 10 million degree structures, and they look like flux ropes, especially this one, like twisted flux rope here. And this one actually looks like a filament, H alpha filament, except that it is hot. H alpha filament is 10,000 degrees, and this is 10 to the 7 degrees. So there is a 3 orders of magnitude difference in temperature. So the question is, all these are really the CME flux ropes, or are they simply hot filaments? And we know CMEs contain cold filament cores or prominence cores. To me, based on this picture, it looks like it is a hot filament. And also, I have looked at some of the corresponding CME images, and I see that these hot flux ropes form a small volume inside the CME flux rope. And it is possible that you can form these flux ropes by the same mechanism, Balahoui and Martin paper in 1980s, that reconnection, slow reconnection leads to filament formation. And these hot flux ropes can also be formed the same mechanism, except that the reconnecting fields are hot already. And one thing I notice in this hot flux rope is that the thermal pressure is the same, whether it is a hot filament or cold filament, which you can see by just using the NT. So for the hot filament, the density is about 10 to the 9 centimeter per centimeter cubed. And the temperature is 10 to the 7 K, so the product is 10 to the 16. And if you look at the cold filament, the temperature is 10 to the 4 degrees, but the density is highest 10 to the 12. So it looks to me somehow, it looks like a, the filament is very hot. But some people, of course, take this as the CME flux rope. So that's what the difference I want to point out. And one of the consequences of this temperature is that, consequence of the low density is that hot flux rope likely become weaker core because in the chronograph field of view, Thomson scattering depends on the density, not on temperature. So hot and cold filament should roughly look the same, except the hot filament should be dimmer than the cold filaments. And Nindos et al. Also found that most of the hot flux ropes seem to be associated with confined flares. That means you form a flux rope and it doesn't erupt. And eventually that hot flux rope erupts as part of a CME. So one of the conclusions of Nindos et al. Is that the hot flux rope observations support the idea that flux ropes pre-exist before eruption. So here is another hot flux rope that existed before the eruption. And this happened to be a huge CME, a GLE producing CME, that is particles accelerated to GeV energies. When you look at the CME, it looks like this. This is the stereo core 1 image. And you have, which normally people identify this, this bright outer structure as the CME flux rope. And then the hot flux rope, you can see as tiny thing, as I mentioned before, they occupy a small volume compared to the whole CME. So it looks to me that it's more like a filament core rather than the CME flux rope, which is also driving a shock and accelerating particles to GeV energies. So I think this difference between the CME flux rope and this hot flux rope should be clearly made. And so my feeling is that the hot flux rope is a small substructure of the CME, whole CME. So if that is the case, then the problem comes, how can this pre-existing flux rope becomes this big CME? My feeling is that the pre-existing flux rope might serve as a seed over which the flare reconnection adds flux to the flux rope and make a bigger flux rope. So that is the only way you can understand the existence of hot flux rope before the eruption. Okay, so how are these flux ropes formed? And this is the famous standard flare model in which you have a current sheet, there's a reconnection, and the reconnection produces a flux rope which leaves the sun, and then it's a post-eruption arcade that is stuck to the sun. And the right-hand side, you see the flux rope that is formed, and the post-eruption arcade represented by these small loops here. So it looks like now you can see the connection between the CME and the flare. Flare is this post-eruption arcade, and the CME is this flux rope. So they are basically produced, both are produced simultaneously by magnetic reconnection. So this magnetic reconnection can be quantified as the total reconnected flux, which is basically if you take one side of the polarity inversion line and accumulate the ribbon area, and the flux within the ribbon area is basically the reconnected flux. And this can be readily obtained from the post-eruption arcade also, because it's basically the flux threading the area under the post-eruption arcade and divide by 2. So you can readily calculate the magnetic total reconnected flux. That seems to be very important in a number of properties of the flux rope. So here is the important connection. So the reconnected flux computed from the post-eruption arcade or the flare ribbons is the same as the colloidal flux of the flux rope that is formed. And this relation, this equality between the colloidal flux of the flux rope and the reconnected flux is the most important relationship that I will be talking during this presentation. So one of the very interesting papers recently published by Brian Welsh is that reconnection does not simply remove the overlying field, the tether, so the CME can escape. Rather, the reconnection produces a change in the force that is acting on the seed flux rope in such a way that the CME is accelerated. That you can understand from this picture, where you can see the top portion of the reconnection region. And the reconnection region itself is tiny, where there is no frozen in condition, but outside there is. As soon as reconnection takes place, you have this field structure, which is not smooth, that I showed in the previous, which is not smooth loops like this, but actually in the beginning, it is very sharp, like this, something similar to the Dungy mechanism that happens in the Earth's magnetosphere. So once you have a structure like this, then the structure will try to move up and become smoother. And in this process, there is a transfer, or there is acceleration taking place of these lines. And also there is a transfer of momentum of the outflow to the CME flux rope. So basically, reconnection adds flux to the flux rope, or the seed flux rope. Not only it adds flux, it also adds mass, because once these field lines overlying the flux rope get reconnected underneath and then become part of the flux rope. So in this process, you are actually reducing the downward tension because of this upward force. And also the hoop force becomes larger, which pushes the flux rope out, because when you add flux to a flux rope, the difference between the top magnetic pressure and the bottom magnetic pressure, the difference increases when you add more flux, because it is proportional to roughly the axial field strength. So essentially what happens is the acceleration due to this resultant force can be expressed in terms of the magnetic field in the reconnection region, the reconnected flux divided by mass of the CME. And for a typical value of 2 Gauss in this region, and a reconnected flux, which is measured typical about 10 to the 21 Maxwells, and CME mass is 2 times 10 to the 15 grams, gives an acceleration of 3 kilometers per second square. So this is kind of a little bit on the higher side, but these numbers are not very accurate, but just order of magnitude. So this is really good. So I think the paper by Welch et al. Produces a very elegant picture of how reconnection plays more than simply removing the tether over flux ropes. And then there is a very nice relationship between the reconnected flux and the CME kinetic energy. Now, CME kinetic energy depends on the mass and speed square. So when you add more mass to the CME and more flux to the CME, and it's likely to have more energy moving out, and that is clearly demonstrated by this picture. And the same thing happens in the flare fluence, and flare fluence also is highly correlated with the total reconnected flux. So you can now see the connection between the flare CME and the reconnected flux. So the conclusion is the reconnection is central in the formation and acceleration of CMEs. And I mentioned about the equality of the reconnected flux and the colloidal flux of the flux rope formed. And this is confirmed from comparing the colloidal flux that you measure at 1 AU. You can basically measure this from in situ observations, and it is shown by Chu et al. In 2007, these black data points here. And also we did some work showing the computing the total reconnected flux in a different mechanism, basically using the post-eruption arcade rather than accumulating the flux under the flare ribbon, cumulative area of the flare ribbon. So this relation is very important, and it clearly shows that this has consequences for theories of CME eruption, because if this relation, the colloidal flux and at 1 AU and the reconnected flux are similar, that means all the possible things that affect the flux rope flux seem to be less significant. For example, if you have a pre-existing flux rope, then if that is the main flux, then the reconnected flux should be much smaller than the colloidal flux. But that does not seem to be the case. So that's why I think, as I mentioned in the beginning, the hot flux rope may be a tiny part of the real flux rope that is erupting. So once you have this reconnected flux, then you can actually determine the magnetic field in a flux rope, because you can fit a flux rope to the white light CME observations, the green structure here, and the surrounding structure is the shock. So once you have the geometrical properties of the flux rope, then you can magnetize it by computing the total reconnected flux, because for a flux rope, especially a force-free flux rope, the axial magnetic field is given by the colloidal flux times the first zero of the Bessel function J0 divided by the radius of the flux rope and the length of the flux rope. So I can simply replace the reconnected flux, colloidal flux by the reconnected flux as I've shown here. And then for this CME, you can actually compute the axial field as
Gopal, sorry to interrupt. You have 5 more minutes.
Okay. So you can see that it is possible to get the axial field at 1 AU or even near the sun, because you can assume self-similar expansion and you can actually compute at any distance from the sun. And also you can find the direction of axial magnetic field from the post-eruption arcade and magnetograms. For example, in this case, it is pointed this way. It's a right-handed flux rope. So you know the helicity sign, and therefore you can get all the components of the magnetic field based on the axial field and the direction of the axial field. So if you calculate the magnetic field near the sun using the method I just described, and if you calculate the magnetic, if you measure the magnetic field at 1 AU, and you correlate them, there is a good correlation. It's not high, but it is significant. For 47 events, 0.51 is significant. So that means you had to have use this kind of flux rope near the sun and propagate it to understand what kind of flux rope you're going to get at 1 AU. So currently, as you know, people are using cone model or some kind of hydromagnetic pulse, and then use that as input to global MHD to get the travel time and magnetic field components at Earth, but it is difficult. You need to use a flux rope because all CMEs have a flux rope. And there are attempts right now to, for example, use the Gibson-Lowe's Ferromac and modify it to make it as a flux rope. But I think the reconnected flux provides an excellent input because it can tell you what kind of axial magnetic field you have and what kind of geometry you have for the flux rope. And for a set of magnetic clouds and non-magnetic clouds, we determine the average magnetic field strength at 10 solar radii as something like 0.05 Gauss, which becomes about 1 to 2 Gauss when you go when you extrapolate it close to the sun. So about 2 Gauss at 2 solar radii seems to be typical. There is another method in which you can calculate the flux rope magnetic field. If you assign the active region helicity is the same as the as a flux rope helicity, then you can derive the magnetic field from the active region helicity. And that seems to be around 0.03 Gauss. It was done by Patsarakos and Yargulis, and which is a little bit less than what we computed, but at least very close to the non-magnetic cloud case. So this magnetic field is very similar to what people have obtained over the years from using, for example, moving type 4 bursts have been used to calculate the magnetic field at 2 solar radii. They all seem to be clustering around 2 Gauss at 2 solar radii. And these are the ones which I just mentioned from the flux ropes. And also people have computed using Faraday rotation. For example, Wood et al. In 2020 obtained about, about 1 Gauss at 2 solar radii. And they are all higher than the ambient field, which is shown by the square below. So the flux rope is basically a high magnetic field structure, and that is confirmed. So let me skip. And then this method of obtaining flux rope structure was made use of by a young fellow by name Sarkar, Ranadeep Sarkar. He introduced additional things from this flux rope. For example, to estimate the impact distance and account for the expansion speed of the flux rope. And based on this, he was able to make an analytical model which predicts the magnetic field vector at 1 AU. And one of the examples is shown on the right-hand side. You can see a very nice fit to the observations. And this is a lot better than other observations, other models, which do not show this nice asymmetric structure. Can we see? Yeah?
Please try to wrap up first. Yeah.
Okay, I'll
almost
try
out of time. Yeah.
Okay. So you can see that it is the red model from Savani et al. Does not take care of this asymmetry in the magnetic field, which happens because of the expansion. And Ranadeep was able to show this happening. So this is an important application of the flux rope for space weather, because once you determine the BZ, you know the speed of the CME already. So VBZ is what determines the strength of the geomagnetic storm. Okay, I'm going to skip the gamma ray part. You can look at it later on. And I just want to end with this slide where the flux rope propagation is also very important, not just the flux rope formation. And for example, the flux ropes, the speed becomes similar to the solar wind speed at 1 AU, even though near the sun, the speed is quite distributed. And then CMEs can be deflected. So the CME is happening from the disk center, but it is going to the south and west because of a magnetic pressure difference surrounding the eruption region. So the CMEs can be deflected. So you normally expect to have a big space weather event, but nothing happens because of this deflection. So you have to worry about CME deflection. And also CMEs can merge. Here there are two CMEs coming from the same active region, so they become merged. And you will be looking at two CMEs, but at Earth you will have only one CME because of the merger. And then also the state of the heliosphere is very important because in cycle 24, the CMEs appear to be much bigger, whereas in cycle 23, the CMEs were smaller for the same speed. This is because the heliospheric pressure in this cycle, cycle 24, has significantly decreased, and that made the CMEs expand more and become kind of magnetically diluted, so their space weather effect is not high. Therefore, the CMEs in cycle 24 have been very mild in producing space weather events. So I will stop here and I will send you the presentation so somebody wants to look at all the other slides that I skipped. Thank you very much.
And thank you, Gopal. It was a very nice review. If you have any questions, please raise your hands. We could have only one question now. Yeah.
So can I ask a question?
Ma'am, there was a hand raised already from II Auditorium. So
Okay.
you could put a question in Slack. So
Okay,
Gopal
let me
can
just
answer
say hello to Gopal Swami. Gopal?
Hi, Vinod. Hi, Vinod.
Hi, how are you?
Good, good. Thank you.
Good, nice to see you. Nice talk.
Thank you. Thank you.
So II Auditorium, whoever is there, please ask your question. And Arnab sir, could you please put your question in either in the Slack or in the chat here? That would be nice.
Okay, sure. Thank you. I shall do that.
Yeah.
Yeah.
II Auditorium. Yeah. Huh.
Hi, this is Shakam. Hello. Am I audible?
Yeah.
Yeah. So I was wondering, you were talking about colloidal flux injection. So my question is, what do you think is the role of colloidal flux injection regarding the self-similar expansion? And if the role is important, then should we expect a differential self-similar expansion during the solar maximum and solar minimum?
No, I mean, it depends only on the helicity that is present in the active region and how much reconnected flux, but it doesn't matter with solar maximum, solar minimum. It just depends upon the free energy available in the active region, and that is basically reflected in the reconnected flux.
Okay. Thank you.
Okay, so possibly one quick question from Arnab. Arnab sir?
Okay, so thank you. So Gopal, you argued that all CMEs involve flux ropes, and they exist before the CME eruption. And for many years, people have been studying coronal loops. Is there some kind of relation between coronal loops and pre-flare flux ropes, or are they completely different things?
No, I think the coronal loops, if they are sheared and they become part of the flux rope in the eruption region, and not all of them, some of them become part of the flux rope. And that's what the reconnection converts the coronal loops into CME.
So
I mean,
the loops are confined to one hemisphere. So are most of these flux ropes also confined to one hemisphere, or sometimes they straddle two hemispheres?
Oh, most of the time they straddle the neutral line in the active region.
Okay.
Flux ropes are on either side, the legs are on either side of the active region.
Okay.
Okay, so I think that would be it. We should move to the next talk. Thank you, Gopal. That was a very nice presentation. And now over to Shravan for the next talk. Shravan?
Hi. Yes, please. Is the next speaker ready? Yes.
Yeah, I'm ready. Can I share my screen?
Yes, please. So we have Kathi Raman from IAA,
Yes.
who's going to be speaking about radio diagnostics of CMEs.
Sorry, please move on to the next speaker. I think I am finding it difficult to change the screen.
Okay, no worries. Please be prepared for the next.
Yeah, for the next talk, I'll be ready.
Yeah. Monica, are you able to speak now? Monica? Okay, so I guess not her either. So do we
Can you
have-
hear me?
Hello?
Yeah, we can hear you, Monica. Please go ahead.
Okay, I don't know. Just a second. I don't know. Let me take down this virtual background.
We can see you.
Hello.
Yeah. Hi, we can see you now.
Okay, I can go ahead.
Yeah, please, Shravan.
Yeah, please, Monica, please proceed. So we have Monica Bobra now, who will speak to us about solar flare prediction, and then subsequently we'll have Kathi Raman. Thank you very much.
So Monica, I'll give you a warning at 20 minutes. So you have 25 minutes in total for your talk. Is that good?
Yep, sounds
Okay.
good.
Yeah, please go ahead.
Okay, so first I'd like to thank the organizing committee for inviting me to speak today. I'm really honored to be part of this 50th anniversary conference series. And today I'll give a review on solar flare prediction using a modern scientific workflow. And by modern scientific workflow, I mean not only modern analysis techniques like machine learning, but also modern approaches to data cleaning, computing, and software development. Okay, so my talk will cover 3 parts. How did we get here? And so in other words, why is machine learning so popular in heliophysics today? Where are we now? And where do we go from here? So let's start with the first part. Why is machine learning so popular today? And to answer that question, I'd like to first take a look at the algorithms themselves. So here's a list of algorithms commonly used in solar physics. And you can immediately see that they were all developed at least 25 years ago. But these algorithms didn't gain that much popularity at the time. Machine learning was not that popular 25 years ago. What really popularized these algorithms is the development of labeled image data, or in other words, clean, organized, easy to access image data with all of the relevant metadata. You can't hear me anymore?
Yeah, we can hear you now. Yeah.
I'm not sure what happened. I had a microphone, I unplugged it, so it should be fine. But yes.
We could hear you all along, actually, Monica.
I see.
Yeah.
Okay. Okay, so labeled image data, so data that's clean, organized, easy to access, has a lot of metadata, is what really made machine learning popular. And 2 of the data sets that are the most famous in machine learning are the MNIST data set, which contains labeled images of handwritten digits, and ImageNet, which is a collection of images that you might see in your everyday life, like cars, bicycles, fruits, vegetables, etc. And these data sets gave the machine learning community an opportunity to showcase the power of their algorithms. So really, data sets are what popularized machine learning algorithms. And we see the same thing in heliophysics. Data sets popularized machine learning applications in heliophysics. There are quite a few early applications of machine learning in heliophysics. For example, people were using neural networks to predict solar flares 30 years ago. And around the same time, people were using machine learning to predict geomagnetic storms and solar cycles. But machine learning was not popular in our field at the time. It was, again, the availability of labeled image data, so clean, organized, easy to access data with all of the relevant metadata that popularized solar flare prediction using machine learning algorithms. Many of the earlier papers used data from SOHO, the Solar Optical Observing Network, and GOES XRS. And people continue to use these data because there are extremely long-running data sets. For example, we have GOES XRS data going all the way back to 1974. But the field really expanded after the launch of Solar Dynamics Observatory, which takes 1.5 terabytes of data a day, and so far accumulated 19 petabytes that now describes an entire solar cycle. So that's where I'll begin my next section, Where Are We Now? And in this section, I will cover flare prediction studies using modern data sets or data sets that are new to our community since SDO launched in 2010. So I'll start with the first study that used SDO data together with a machine learning algorithm. And for that, we used vector magnetic field data with a learning algorithm called a support vector machine. But we didn't use the image data directly. Instead, we isolated the active regions and calculated 25 physical features that describe these regions, like, for example, the current helicity, magnetic flux, Lorentz force exerted by the active region on the solar atmosphere, etc. And we did this for every active region at every point in time. So we ended up with 38 million features describing 2,100 active regions. And then we posed the problem quite simply. Okay, so this is a plot of the GOES X-ray flux for an X-class flare in 2017. And on the x-axis, we see time, and on the y-axis, flux in units of watts per meter squared on a log scale, and the two different color bands are two different wavelengths. And we asked a very simple question. We said, okay, if we looked at the value of our features here, can we predict whether there'll be a flare 24 hours later here? Yes or no? And then we used a support vector machine to analyze these data. So how does a support vector machine work? So suppose we have a two-dimensional feature space. So on the x-axis, we have the area of an active region, and on the y-axis, we have the flux. And suppose we plot all of the active regions that didn't flare with an X, and all of the active regions that did flare with an O. So all the support vector machine does is draw a line called a decision boundary between these two classes. And it draws that line where the distance to the nearest example, the nearest positive and negative example, is maximized. So these little yellow vectors are called support vectors. So that's pretty simple. But of course, we don't have a two-dimensional feature space. We have a 25-dimensional feature space. And the support vector machine is not drawing a line, it is drawing a hyperplane that separates these two classes. And of course, they're not perfectly separable like in this example. So you have some misclassifications. And you can assign penalties for those, and the algorithm will try to minimize the penalties. So this whole procedure that I described here trains the model. And in our study, we took 70% of the data, so about 1,500 active regions, to train the model. Okay, so now that we have a trained model, now we have a trained machine learning model, and it can take a new example for which we do not know the answer, plot it in this n-dimensional feature space, figure out which side of the decision boundary it's on, and issue a prediction about whether this point corresponds to a flaring active region or a
Join करने वो खाली नहीं था.
So we tested our model on the remaining 30% of our data, or about 600 active regions. And we ended up with some pretty decent results. Our accuracy was 0.92, which seems good, but for rare event prediction, a high accuracy can be misleading because you can get a very high accuracy just by predicting no all the time. So we also calculated a skill score called a true skill score, or TSS, that quantifies how much better you do versus predicting no all the time. And this particular skill score goes from -1 to 1. So -1 is the worst possible prediction, so getting it wrong all the time. +1 is perfect prediction, and 0 is the same as guessing randomly, so no skill. So our true skill score for this study was 0.76. And scientifically, we learned that out of all the features we calculated, the current helicity was the most correlated with flaring activity. So this is a really simple initial approach to the problem. And a lot of studies really improved upon these results. These are the studies that are really driving progress in the field. And there are so many studies because everyone is looking at different features, using different learning algorithms, looking at different timescales. And I can't go through each one of these studies, but I want to take a closer look at one class of studies looking at time series data. And in particular, those studying time series data using a learning algorithm called long short-term memory, or LSTM. And this is how those studies pose their problem. So suppose we calculate a particular feature of an active region, like the magnetic flux we discussed before. And suppose we track that feature over time. So now we have a time series. But since we have a lot of features, we have a lot of time series. And all of these time series describe just one active region. But suppose we also look at all of the other active regions on the sun at the same time. Does the collective evolution of all these time series data help us predict flaring activity? So we can investigate that with an LSTM. Okay, so what is an LSTM? So if we look at the magnetic flux as a function of time for just one active region, right here, the first study that I mentioned only learned the relationship between one discrete data point and an outcome. An LSTM, very simply, learns the relationship between a sequence of data points and an outcome. And it does this by assigning weights to each of these points based on their relationship to one another. LSTMs also have the unique ability to forget data points that are irrelevant. And this algorithm turned out to be quite successful and boosted predictive capacity to a high level. And through all of these efforts, we may now be approaching the limit of how well we can predict flares using magnetic field data alone. And for that reason, studies began incorporating additional types of data into their analyses. For example, studies began using magnetic field data together with features derived from images of the chromosphere, such as UV brightening. And then the natural next step is to also incorporate EUV image data. So many of the flare prediction studies we see today use multi-wavelength data, and specifically multi-wavelength data together with convolutional neural networks. And we're seeing a lot of experimentation with different types of convolutional neural networks. Okay, so what is a convolutional neural network? It is at its core a series of very simple image processing steps. So first you take an image. This is an image of a flaring active region. Then you convolve it with a kernel, threshold it, downsample it, and vectorize it. So now you have a vector of all of the values in the downsampled images. And the learning part happens here. So the idea is to learn what filters will give you, in theory, a simple and general representation of a flaring active region. And because a convolutional neural network is a series of very simple image processing steps, you can set it up in basically an infinite number of ways. You can perform a bunch of different you can go through the convolution, threshold, and downsampling steps over and over again before you vectorize. And people are experimenting with all of these different architectures. But regardless of how you set it up, you ideally want to end up with a bunch of simple general representations of flaring active regions and quiet active regions. And if we achieve that ideal, we can then take an image of the sun from right now, run it through these simple image processing steps, compare it to our collection of simple general representations, and accurately predict whether an active region will produce the flare. But there are a few things that we need to look out for when we're building these convolutional neural networks, because our data is different from the typical ImageNet data in 3 major ways. So first, the photospheric magnetic field images map a vector, not a scalar field. There are actually very few vector field images in the scientific community. Some Earth observatories take vector field images of wind data, but the vast majority of people use scalar field images, basically images that only vary in brightness. Second, images of the solar atmosphere can span 5 orders of magnitude in dynamic range, but most people use images that span 2 orders. Most people that are using convolutional neural networks are using them on images that span 2 orders of magnitude in dynamic range, or 256 values of brightness. So in other words, the typical image we would take on our phones. And finally, solar image data have unusual signal to noise properties. For example, we have more noise in the transverse component of the magnetic field than the radial component. And for the EUV and UV image data, the signal to noise is a function of various instrumental properties, like the thickness of the physical filter on the instrument. So we need to build convolutional neural networks that address these 3 properties of solar image data. Otherwise, they'll pick up on physically meaningless attributes of the data, like, for example, calibration artifacts or bad pixels or exposure time. Successful implementation, however, can help us discover new, subtle pre-flare signatures in the image data. Okay, so that covers image data. But image data is not the only data type useful for flare prediction. People have also used spectral data to predict flares. This is a spectrogram of magnesium-2 taken by the NASA IRIS satellite that captures an X-class flare. And this shows 10 different features calculated from this profile. The authors calculated these 10 features for each of 9 flaring active region spectra within a 30-minute margin of flare onset. So studies like this show us that in the era of multi-messenger astrophysics, image data is not the only data useful for predicting solar flares. We can also use other data types, many of which remain underutilized in flare prediction, like radio data. Ultimately, we will see the biggest increase in predictive capacity from using physically meaningful, information-rich data sets. Okay, so that brings me to the last section of my talk. Where do we go from here? And I will pose this as 4 challenges we're facing today and how to overcome these challenges. The first is the challenge of cleaning data. Machine learning studies require a lot of data cleaning, getting rid of bad data, organizing data, normalizing data, dealing with sparse data, dealing with legacy data, etc. Worse, how we clean the data has a huge impact on our final results. The accuracy scores of even the best image classifiers are highly sensitive to the minutia of the data cleaning process. And there are a number of solutions for this problem. One is to create machine learning ready data sets. In other words, an ImageNet for solar data. And we do this already in our community. A number of people have created analysis ready data sets. And as we've seen, this creates even more interest in data from these particular instruments. We also need to serve data in analysis-ready formats like HDF5 or ZAR. FITS was an adequate format when it was invented, but now that we're taking terabytes of data a day with instruments like SDO, DKIS, the Vera Rubin Observatory, the Square Kilometer Array, we need data that transports well, compresses well, and is easy to break up into chunks for parallel computing. Another is the challenge of moving data. Moving data is difficult for a few reasons. One is slow network speeds. It is difficult for researchers to download large data sets. On the other side, it is also difficult for instrument teams to serve large data sets. Second is limited storage. Even with institutional help, it is difficult to store large data sets that consist of hundreds of terabytes or petabytes. And finally, some researchers lack adequate computational resources. These 3 hurdles prevent the scientific community from maximizing the scientific result from large data sets. And the solution is to shift the way that we do research. In our current paradigm,
Monica, you have 5 more minutes. You have 5 more minutes.
Thank you. In our current paradigm, we move data over a network to analyze on a local machine. But the problem here is that the data are large and the network is slow. Alternatively, we can move our analysis software, which is lightweight, to a shared external computing platform, equipped with multiple mission data sets, plenty of compute and storage, environments for installing and using general purpose scientific software, and plenty of compute. And these science platforms are free researchers from worrying about network speeds, storage, and compute, and allow them to pursue compelling scientific studies. And the astrophysics and earth science community already uses Science Platform. In particular, the earth science community uses a platform called Pangeo, which has completely revolutionized the way they do research. But we have yet to use science platforms in heliophysics. A third challenge is the challenge of software development. Machine learning studies require writing a lot of analysis software. And software development is really time consuming for a number of reasons. First, researchers rewrite the same code over and over again for basic data analysis like data retrieval or coordinate transformations, and this wastes a lot of time. 2 is that researchers work with a lot of legacy code that's slow at scale. And third, researchers find it difficult to reproduce scientific results. There are a lot of figures about reproducibility out there, but one study estimated that 70% of scientific results in physics and engineering are not reproducible. And the solution is to use version-controlled, unit-tested, openly developed, and openly available scientific software. In particular, Python provides a rich and mature ecosystem of scientific software for heliophysics, machine learning, and parallel computing. And the final challenge is the challenge of interpreting machine learning models. The practical successes of machine learning algorithms are not often matched by successes in interpretability. And this has become an issue within the machine learning community. And the solution here is twofold. First, begin an analysis with a simple model. We've seen from the literature that the fanciest model does not necessarily give the best results. And the second is to use tools specifically designed to solve this problem. There are a host of model agnostic interpretation methods available today, and they give us more insight into the behavior of the learning algorithm. So that's the end of my last section, and here's my summary slide. So how do we get here? Data sets, not algorithms, popularized machine learning and heliophysics. Data sets gave the machine learning community an opportunity to showcase the power of their algorithms. Where are we now? The highest performing learning models use physically meaningful and information-rich input data. They're not necessarily the fanciest models. Furthermore, we have a multitude of data types available for solar flare prediction, and many data types remain underutilized. And finally, where do we go from here? We must modernize our approach to cleaning data, moving data, and developing software to maximize the scientific return from large data sets. And that's it. Thank you so much for listening.
That was a wonderful talk, Monica. It was also on time. It was amazing. We have a couple of questions. Dipankar, please go ahead.
Excellent talk, Monica, and also setting the next generation attitude, what it should be for heliophysics. My question is, you mentioned about these 25 parameters, their optimization and so on. Could you rank, these parameters which are more crucial than others? And also I was wondering how important is the new flux emergence in this entire scenario and how well you are able to capture that?
Yeah, so yes, absolutely, you can rank it. There are many different ways to rank the importance of features. Feature ranking is an important aspect of machine learning. We did that in our study. We found current helicity to be the most predictive. We also found that we don't increase predictive capacity much more after using about 3 or 4 features. So we don't really need 25. As far as emerging flux, that is, I think, an active area of research, being able to adequately capture flux emergence as a feature is a difficult thing to do. So I think that is an active area of research and a good research topic.
Thank you. Thank you.
Okay, so next question, Hari Haran, I think. Hari, please go ahead.
Hi, Monica. It was a nice talk. So I was just confused. So your model is based on the support vector machine, or are you developing a CNN-based model? And secondly, if you have done a support vector machine as your model, why was it chosen? Because its support vector machines usually tend to fail for large data sets and normally take a longer time for training the data sets. So why didn't you go for a KNN or a decision tree or something like that? Can you comment on it?
Okay, yeah, so I'm sorry if it was confusing. I was trying to go through a review, so I was starting with the most simple model. So yes, in our initial approach, we did use a support vector machine. I think we ended up using it because it was fast. I think that this is why people end up using one machine learning model over the other. You have to balance sort of accuracy and speed and interpretability and figure out where you want to hang out among those things. So we chose it because it was fast and accurate. We have implemented convolutional neural network as well. That was the study by Jonas et al. I worked on that as well. And that was a shallow network. And a lot of people have found that a very simple ConvNet architecture, something very shallow, very simple, works just as well as some of the deep learning methods. And I personally think it's because the solar image data are, it's a complicated data set for the 3 reasons I outlined. And so using a deep neural network might be focusing a little bit too much on the noise.
Yeah, so next question is from Dibyendu. Dibyendu, please go ahead.
Hey, Monica, really enjoyed your talk, and it's great to see you after so many years. So I have this question about predicting the timing of flares. So this is the holy grail in solar physics, and one would think that being such a powerful tool, machine learning can take you there, where we should be able to predict, maybe based on time series data, when is it an activation going to flare. Are the studies directed towards this? Do you think there is a potential that we can in fact answer this question?
Yes, I think that there's potential that we can answer this question. Yes, there are studies directed towards this. One of the reasons that there are so you can ask, can we predict if there is a flare in 24 hours? Can we predict if there's a flare within 24 hours? Can we predict if there's a flare within 1 hour? So everybody is posing the question differently. I think that we can get there. I think our biggest limitation is actually the data set. If you look at progress in terrestrial weather prediction, they benefit from having multiple satellites that are sampling the weather from multiple vantage points. And we just have one vantage point with SDO. We don't even know what's going on in the back of the sun. So I think that's our biggest limitation. But if we had more data, I think we could get there, yes.
Thanks.
Yeah, so the final question, Alphonse, please go ahead and ask your question.
Okay, thank you, Monica. That was very nice. And my question actually is kind of similar to Dibyendu's. I'm wondering if there are algorithms that do a pretty good job at predicting flares that you've seen. And if not, are there algorithms that you've seen tried and you can say pretty confidently that they do not do a good job at predicting flares?
Well, I think, a lot of algorithms have done a really good job, which is why I mentioned that I think we've maybe reached our predictive capacity using magnetic field data alone. So yes, I think convolutional neural networks have a lot of promise. I think, as it says on this slide right here, I think it's a balance between the algorithm and the input data, because if you're not giving it good, if you give it garbage in, you're going to get garbage out. So I think featureizing the data is really the most important part, in my opinion. And the algorithm kind of comes second to that.
So basically, if I ask you, is there going to be a flare in an hour? Is there an algorithm you could point me to that would say, yeah, there's a 90% chance that it's going to be there?
Yeah, a lot of people, I mean, this is a lot of the studies that I cited are doing this exactly. So yes.
Thank you.
Okay, so that would be it for question and answer session. Monica, I have a lot of questions on the chat, so you could answer them. If you're on Slack, you could answer them there. People could put the questions there. And thank you very much for this wonderful talk. Now I give it to Shravan for the next talk.
Thanks again, Monica. Kati Ravan, can we? Yes, amazing.
Can you see the screen?
Yes, please begin. Thank you.
You can keep it closer.
Hello, everyone. I'm going to talk about the radio observations of CMEs. Earlier, I think today morning, Gopal Swami has talked a little bit about that, but I was unable to attend that talk because of some technical issues. And I thank our colleagues for arranging this conference. And my plan of the talk is I will be giving a brief summary of the CME properties and then the imaging and the spectral and polarimetric observations of the thermal and non-thermal components associated with the mass ejections in the radio domain. So a CME is a discrete brightening observed in the field of view of white light coronagraph, which always moves outward from the sun into the heliosphere in the time scales of tens of minutes to hours. So it's a large scale plasma entrained on an expanding magnetic field. We can simply identify using the running difference images or in time-lapse movies. It's a simple cartoon. I think when the CME comes out from the sun and it goes all the way in the interplanetary medium, it can engulf any planet on their way. And if they happen to be, if the magnetic field of the CMEs happen to be reconnecting with the planetary system, it can enter into the ionosphere of that particular system, and it can give rise to geomagnetic storms, which are harmful for the technological systems which are deployed in space and on the ground. So that's why I think the National Weather Service, they came up with a plan. And as per that, the space weather refers to conditions on the sun and in the solar wind, magnetosphere, ionosphere, and thermosphere that can influence the performance and reliability of spaceborne and ground-based technological systems that can affect human life and health. So I think several satellites were launched to observe the coronal mass ejections. One of them is the LASCO C2, and it gave rise to some 10,000 CME observations. And based on the statistical analysis, the average properties of the CMEs were found out. And the width is 41 degrees, mass is about 10 power 15 grams, and the speed is around 490 kilometers per second. And the kinetic energy is 2 times 10 power 30x. And the source location is limited within plus minus 47 degrees heliographic latitude. And the occurrence rate is 1 to 5 per day, and it varies with solar cycle. Since the CME travels in the interplanetary medium and it connects the Earth, so one has to observe from the initiation of the CME till it reaches the Earth or any planetary system and beyond. So I have given a comparison. The CME close to their onset are studied well with white light coronagraphs. On the right-hand side, I have shown the LASCO C2 coronagraph. And usually coronagraphs come with occulters. So the structures related to the CME on the disk are studied with either extreme ultraviolet or the infrared. And let's say the CMEs, they give rise to solar radio emission also. I have given the comparison with the Gauri-Bindu radio heliogram obtained on the same day. The left-hand side panel shows that. And I have given an artificial occulter on top of the radio heliogram. One can see a very good spatial correspondence between the structures A and B on the east and then west limb of the sun. And in addition to that, if you see the radio heliogram, you can see I have marked with C, both on the disk and off the limb sources can be observed simultaneously. So it is an excellent complementary thing for the data. And the green color circle, dotted circle I have shown here corresponds to the VELC field of view, that is 1.05 R0 to 3 solar radii. So our radio heliograms would be a very good addition for this. And then one can study CMEs from the initiation by combining the VELC and radio data. And since the CME travels in the interplanetary space, they give rise to shocks in the interplanetary medium, and the shocks can be observed with radio spectral data in the hectometric and kilometric band. And the people use the radio interplanetary and scintillation observations also to track the CME in the interplanetary medium. And in situ observations are radio as well as particle counters and magnetometer data. So CMEs can be studied with white light and radio as well. And the non-thermal emission like type 1, 2, 3, 4, and 5 in the meter band can also be used to understand the CME properties. So this is I think we thought of whether the mass of the CME can be estimated using the radio data. I think Gopal and Kundu has given a very good, I think, example in 1992. So the right side image shows the radio difference image taken during 2029 to 1955 UT, subtraction of the radio heliogram. It was observed on by the Clarke-Lake radioheliograph at 73.8 megahertz observations. They are given the formula to estimate the electron density. At the bottom, you can see. So that's a nice formula. And then, so we thought of using the same formula and then the observing technique to estimate the coronal mass ejections mass using the Gauri-Biddur data. There was a CME observed by LASCO on November 24, 2000. It was a halo CME, and the speed was about 1,300 kilometers per second. So we have observed the same event with the Gauri-Biddur radioheliograph. This is on the right-hand side. We have taken the image on at 455 UT. The brightness temperature is around 4.2 times 10 power 6 Kelvin, which is on the west limb, and the contour interval is 0.5 times 10 power 6 Kelvin. And after 10 minutes, 5.5, we have observed it again. And there is a small structure that is developing at the west limb. And then you can see the enlargement of the feature on the west limb at 515 UT. And at 525 UT, you have seen a nice CME, which is almost resembling with the white light CME. So although the brightness temperature has not changed on the east limb, so the brightness temperature enhancement you can see nicely on the west limb. So we have also taken the difference image at 5.5, 5.15, and 5.25. I think I have shown with green color, orange, and red color. And using the position vector of R1, R2, R3 of the enhancements related to the radio CME, we have marked the position, and then taking the difference between R3 minus R2 and R2 minus R1 by T2 minus T1 will give you the average speed in that plane of the sky. So we have tabulated the values, and the velocity is approximately 1,087 kilometers per second in the 5.5 to 5.15 UT, and the other one is 1,185 kilometers per second. We have estimated the mass also, and the average value is around 4.4 times 10 power 16. So both mass as well as the speed can be estimated using radio data like the white light data. So this is one of the examples. And as you know, I think all the 2D observations, they suffer projection effects. So in order to overcome, people have come up with 3D models, and some of them I have given here: type pointing technique, forward modeling, reverse reconstruction. Most of these techniques, they use stereo LASCO data or the data obtained at multiple viewpoints. The same way, I think we try to use the radio data because they also suffer from 2D projection effects. So similarly, like the white light, we can come up with some 3D models in the radio. We thought about it, and then we used ray tracing technique using by assuming a background electron coronal density model and appropriate density distribution for the coronal mass ejections as well. This is the basic equation we use. The observed brightness temperature is nothing but the electron temperature of the corona multiplied by 1 minus e power minus tau plus the coronal temperature in e power minus tau. That tau is the optical depth, which is the integral of the absorption coefficient times the DL, that is the line of sight depth, or the ray through which the medium, the DL is the integral path length. And absorption coefficient is directly proportional to electron number density square and inversely proportional to the observing frequency, refractive index, and the electron temperature to the power 3 by 2. And we know this refractive index formula as well. And the FP is the plasma frequency, which is directly proportional to NE because other values are constants. So I think we usually trace the ray using this equation mu1 by mu2 times S1 minus S2 equals KL, where S1, S2 are the incident and the emergent ray and the normal ray vector. So we have used the nuclear density model. In principle, any density model related to the corona can be used, and we assumed a Gaussian distribution for the coronal mass ejection. So we studied an event to estimate the true mass of the CME because we do not want to make any assumptions using this 3D technique. On the left-hand side, we have shown the white light coronagraph image, LASCO C2 image. On top of that, the radio contours are superposed. And the structure 1 shows the CME before its eruption. It's like a pre-eruption swelling. And we have reproduced the image. I have shown that on the right-hand side. About 14 sources were used to reproduce the image. And only 4 sources, S6 to S9, correspond to the CME structure. And column 2, we have given the position coordinates of those sources to reproduce that CME and the size of that CME features. And we have estimated the average density about 2.6 times 10 power 7, and the total mass is about 2 times 10 power 15, which is 1/4 of the mass of the LASCO CME. So similarly, the same technique we tried to adapt and then to estimate the true speed of the CME in the 3-dimensional space. We have taken the event on 21st January 1998. And if you take several images of the solar corona and try to reproduce them as a function of time, we can make use of that. So this image was obtained at 5.1 UT, another one was at 6.1 UT. You can see a very gradual increase in the size, and it is like looking like a halo CME. So we went ahead and then taken the difference image. There is a nice overlap and nice spatial correspondence between the two.
Kadir, you have around 2 minutes.
Oh, okay.
Yeah.
So with we have reproduced the structure at 5.1 and 6.1 UT. About 15 or 16 sources were used to reproduce. And then the sources corresponding to that particular CME enhancement was M18 to M13. By summing up the mass of all these structures, we estimated the mass of the CME. And then the position vector of the CME was also estimated. Since this CME was associated with the disappearing solar filament, we have used its position to estimate the position vector of that particular location. Then making the difference of these two, we have estimated the true speed of the CME. So we have estimated the line of sight component to be 318 kilometers per second using the X component of that position vector difference. And Y and Z component gives the plane of the sky, which is 485 kilometers per second. So we try to understand whether any pre-eruption signatures could be determined using these observations, using the reproduction. And then a quadrant-wise density enhancements were chosen. And then we plotted in all 4 quadrants. You can see the nice enhancement only in the southeast quadrant, which is about 18 times, whereas the other quadrants, it is very nominal. So this density enhancement was used to calculate the mass injection rate, which is about 8.8 times 10 power 15. And the CME mass is close to 6.5 10 power 15. So now I move on to the non-thermal part. And when the CME moves after its ejection, it gives rise to shocks. And type 2s are the signatures of shocks. One such a signature is given here. This event was observed on 23/5/2007. These are this is a single type 2 event. The bottom one is the fundamental and the top one is the harmonic. So we want, there is a long standing debate that whether the type 2s are driven by flares or CMEs. We wanted to understand that without assuming any density model for the height determination, and then to get rid of this projection effects. We wanted to compare the height of the type 2 with respect to the CME leading edge. We have used the simple kinematic equations and then the X-ray data to find out the location of the CME leading edge. Out of 41, 38 events were found to the type 2 burst locations were just above the CME leading edge. So we were unambiguously established that CMEs are the drivers of type 2. So the radiospectral and polarimetric observations, we try to identify the features of the CMEs responsible for the shock.
Kadir, could you wrap up fast? Almost out of time.
Yes. I think this is the very nice example of a type 2 event, which is a split band type 2. There are 2 successive type 2s. Using this, we could find the location of, there are 3 possibilities, whether these successive type 2s are driven by flares or flare CME or only 2 CMEs. So using this analysis, we established that the CME, the second CME, which was following the first CME, interacted with the flanks of the previous CME and the streamer, give rise to the type 2 split band. So this is the location where it got, where the shock has been generated because of the interaction. And the coronal B estimate also we can do using the radio by combining the extreme ultraviolet, U and radio, spectral as well as imaging observations. We estimated the magnetic field strength in the height range, radial distance range 1.1 to 2.3 R0. Using the combined data, the magnetic field goes as R to the power minus 2.2. So even type 4s also can be used to study, but because of time limitation, I stop here.
Yeah, thank you, Kadir. We have time for one question. Please raise your hand. Yeah, Hari, go ahead.
Hello, can you hear me?
Yes.
Okay, so I had the question that so you mentioned about the thermal emission from the CMEs. So what percentage of CMEs give up thermal emission, and is that a sensitivity issue that we don't see thermal emission from all CMEs if it is not the case?
I think our observations are very limited because we are having the transit instruments. We do not have the continuous coverage. And if minor non-thermal components are present, then because of the dynamic range, we may not be able to image the CME thermal component. If we are having the high cadence and if we are able to separate out the non-thermal part, then we can increase our observing capability or to detect the number of CMEs. It is possible, but with the sensitivity as well as the dynamic range also plays a very crucial role.
Okay, thank you, Kadir. That was a very nice talk. Now over to Shravan for the final talk.
Hi, is Anshu online? Can you please?
Yeah.
Come on now.
Okay, so the last talk is on again radio bursts and CMEs from Anshu Kumari for this session. Thanks very much, Kativaran. And so now we're yes, please begin. Thank you.
Thanks, Shravan. Thank you, Gopal and Katiravan sir, for setting the stage for me. Hi, I'm Anshu. I am currently working as a postdoctoral researcher at University of Helsinki with Professor Emilia Kilpua. I work on time-dependent data-driven kernel modeling and solar radio transients. In this talk, I will present our recent work on type 4 radio bursts and their association with kernel mass ejections in the solar cycle 24. Kernel mass ejections are large eruptions of magnetized plasma from the sun. They are often accompanied by radio emission. The video here shows a CME as seen by SOHO LASCO C2. The white circle is the radius of the photospheric sun, and this is the size of the crater, which is around 2.2 R0. The sudden emission at 3 UT is a CME. These radio emissions are generated by energetic electrons, which are accelerated during these massive eruptions by various emission mechanisms. The image here shows the dynamic spectra of the sun on 19th May 2007. The top two panels are with space-based spectrographs, and the bottom two are with ground-based spectrographs. So this sudden enhancement, these brightness in the solar dynamic spectra are called radio bursts, and it can be classified as type 1, 2, 3, 4, and 5 bursts. The most common radio bursts associated with CMEs are type 2 and type 4 bursts. So type 1 bursts are non-thermal radio emissions generally associated with active regions. Type 3 bursts are very rapidly varying bursts of radiation at meter wavelength that show fast drift in the dynamic spectra from high to low frequencies. Type 3 burst represents the electron acceleration. The electron beams travels through the corona in interplanetary space along open magnetic field lines as shown here. Type 2 bursts are considered to originate from plasma waves excited by MSD shocks and converted into radio waves at local plasma frequencies, and is harmonic. So it is a slowly drifting burst as seen in the solar dynamic spectra. They are the direct diagnostics of MSD shocks in the solar atmosphere. And this is called type 4 burst. Type 4 bursts are broadband continuum at decimeter and metric wavelength, and it usually lasts for longer durations. Depending upon their spectral and imaging characteristics, it can be classified into two categories, moving and stationary type 4 bursts. These bursts have different emission mechanism, for example, plasma, synchrotron, and these in the dynamic spectra, stationary type 4 bursts show no drift feature at all, while the moving burst looks something like this. So these two figures shows how a stationary and a moving type 4 burst would appear in solar dynamic spectra. In this work, we did a detailed statistical study on the relationship between type 4 emission and their association with CMEs in the solar cycle 24. We used the event list provided from the SWPC, Space Weather Prediction Center, and we picked out all the type 4 bursts from there. For CME data, we use CME detected by SOHO LASCO stereo A and B core 1 and core 2 coronagraph. We extensively use CDO CME database and SEEDS database. we use the temporal and spatial association to relate the occurrence of type 4 bursts with CMEs. We use two criteria. The first one, the active region associated with the CMEs and type 4 burst should be the same. And two, a CME should appear in LASCO or stereo field of view within 2 hours of the start time of the type 4 burst. So the algorithm which was used to obtain the final list is described here. So the input for the algorithm were SWPC event list and the CME list from all the coronagraphs. And then a common date and time for the CME and type 4 bursts were identified based on their temporal and spatial correlation. We also divided the type 4 bursts into 2 subgroups, that is moving and stationary based on their spectral characteristics, that is drift rate and duration. Because we did not have 24-hour radio imaging observation, so we couldn't use it. The only option we had was to use the spectral based classification, which has its own limitation though. So there were total 16,107 CMEs as detected by LASCO and only 446 type 4 bursts. And almost 80% of the type 4 bursts were stationary based on the spectral based categorization. The figure here shows the distribution of CMEs and type 4 bursts in this solar cycle. We use the data from 1st January 2009 to 31st December 2019. All the distribution shows Gaussian profile with the peaks around Jan to June 2014, which was the maximum of this solar cycle. Around 81% of the type 4 bursts, including both stationary and moving, had white light counterpart, whereas only 2.2% of the CMEs had any radio signatures as type 4 bursts. So this says that almost all the type 4 radio bursts had a CME association. However, the vice versa is not true. Approximately 91% of the moving type 4 bursts were associated with CMEs. That is because moving type 4 bursts are said to be originated from the electrons being accelerated or trapped inside the flux rope. However, only 78% of the stationary type 4 bursts were associated with CMEs. That also indicates that stationary type 4 bursts could come from the leg of the erupting flux rope. We categorize all the CMEs based on their linear speed and angular width as fast, slow, wide, and narrow CMEs. The CMEs with linear speed greater than 500 km per second were put in a category of fast CMEs, and the rest were called slow. Similarly, for the CME categorization on the basis of width, for the CMEs with a width greater than 60 degrees were called wide CMEs, and the rest were categorized as narrow CMEs. And the histogram here shows the distribution of moving and stationary type 4 bursts with different type of CMEs. We found that around 50% of the moving type 4 bursts were associated with fast and wide CMEs, and the rest 50 were evenly distributed among all the other type of CME. So this is very similar to how type 2 association with CMEs looks like. So type 2 bursts are also very most commonly associated with fast and wide CMEs in meter wavelength. However, the stationary type 4 bursts were unevenly distributed among all type of CMEs. All type of CMEs, like if you could see here, fast and wide and fast and narrow and everything else. So which says that this also indicates that stationary type 4 bursts could come from the leg of the flux rope and not from the electrons trapped inside the flux rope. And there are very less type 4 bursts which were associated with fast and narrow CMEs, which can be seen here. The duration and drift rate of the radio bursts were estimated for both type of type 4 bursts. So the first two are for the duration. This is drift rate. Drift rate could only be estimated for the moving bursts, since stationary bursts could not show any drift. So the duration was estimated using the start and end time of the burst as mentioned in the SWPC event list. So type 4 stationary bursts could last from few minutes to almost a day. So those are called type 4 storms. And there are very few type 4 storms which could go for more than 14 hours. For moving type 4 burst, it only lasted for less than an hour, except two exceptional case we had, which is not included right now in this figure. And then this is how the drift rate of the moving burst looks like. The drift rate of the moving burst was calculated by using the start and end frequencies of the burst and the duration of the burst. So for moving type 4 burst, the drift rate varies from 0.03 megahertz to almost 2 megahertz. However, only 5% of the moving burst had drift rates more than 0.5 megahertz per second. So these are high frequency, very fast drifting bursts, and individual case studies has to be done to study the occurrence and why occurrence of these bursts and why they have this unusually high drift rate. We haven't done individual case study yet for these events. So this figure here shows the correlation between the occurrence of CMEs, type 4 bursts and sunspots. So the occurrence of type 4 bursts had around 92% of correlation with the CMEs, which is also the same number we got for moving type 4 bursts. So that indicates that almost all the moving type 4 bursts are associated with CMEs. The table here shows the occurrence and the association of CMEs with moving and stationary type 4 bursts, and it shows that most of the moving type 4 bursts were associated with fast and wide CMEs. To summarize and conclude the work done, we performed the first comprehensive long-term statistical study of type 4 radio bursts during this solar cycle 24. Out of the 446 type 4 radio bursts, around 81% of these bursts were accompanied with white light CMEs, and the rest 18% were associated only with flares. And in this 18%, 3% had occurred during the end phase of a flare. That means during the decline phase of the flare. We haven't looked into detail of those individual 3% of the bursts yet. So our study found that 91% of the moving type 4 bursts had CME association. And type 4 bursts were more associated with fast and wide CMEs, which can be seen here. To precisely find out if a radio burst is moving or not, one should use radio imaging observation. But in the lack of those, we use the spectral-based classification. And due to that, we had a few events which were classified wrongly in wrong group. Our analysis showed that moving type 4 bursts were more frequently associated with fast bursts rather than slow CMEs, and with wide rather than narrow ones. In turn, the occurrence of stationary type 4 bursts did not depend upon this speed of the CME, though it did depend upon the width of the CME, because it was more frequently associated with wide CMEs. The high association of type 4 bursts with CMEs indicate that type 4 bursts, when present, can be used for studying the electron acceleration location as well as the CME kinematics during the early phase of the eruption. So since we had the limitation, because we didn't have the radio observation, as a follow-up study, we used radio images to find the association of only moving bursts. So for this, we used radio imaging from NASA radio heliograph, where we constructed a list of list of all the type 2 and type 4 bursts, because these are the two bursts which are associated with CMEs. And we defined the association of these bursts with CMEs, and we studied the properties. And we also determined the connection of classical type 2 bursts and type 4 bursts, whether it's moving or not. So we found that all the type 2 bursts were moving in radio images. However, not all the type 4 bursts were moving. So the observation presented here shows a moving source. So what we did is we did.
Actually, you're almost out of time.
Almost done.
Yeah, fine.
So what we did was we had 1D, this is 1D profile from NASA. So this is in east-west direction, this is in north-south direction. So we track down the source movement. So if it moves in a constant, if it doesn't show any drift, for example, like this, and it shows something like this, we say it's a stationary burst. And the moving burst, how we classified the moving burst was it should move in the east-west or north-south direction. So the majority of the events which we are studying here were associated with wide CMEs. It indicates that there is a strong lateral expansion during the early stage of eruption, which may play a key role in the occurrence of radio emission, which is observed associated with the CME. This also indicates that that's the reason not most of the moving burst or stationary type of bursts were associated with narrow CMEs. So type-4 burst may therefore be used to estimate CME expansion or the expansion of the electron acceleration region behind the CME or the leading edge of the CME, depending upon which kind of burst it is. And it can be used for estimating the early kinematics of the CME if there is no other observation available. So yeah, thank you.
Thank you, Anshu. It was almost on time. We have time for one question. Please raise your hands and then you can unmute yourself. Questions? I don't see any hands raised. There's a question on chat by Tushar. So Anshu, Tushar asks, could we say that high-speed streams cause type 2 burst or other burst events also take place?
What is the question?
Anshu?
Yeah, I'm just reading the question.
Okay, fine. Yeah.
What other bursts? So there are only two bursts which could be associated with CMEs, type 2 and type 4. So we can also see type 4 burst when there is high speed CMEs. So yeah.
You also have a question by Gopal.
Yeah. Just moving type 4 burst required.
So Anshu, so you have 10% of moving type 4s are not associated with CMEs.
Yeah.
But moving type 4 needs you need to have some kind of moving magnetic structure with non-thermal particles trapped in it. How do you get them?
Yeah, so it could be either related to a failed eruption, but we are not sure because we didn't look at individual case studies. However, we are now looking into a list of, so we also found that around, for a similar study for type 2, that around 20 type 2s in this solar cycle had no CME association at all. So we are looking into these 10% type 4s and those 20 individual type 2s in detail, because what we suspect right now is those could be because of failed eruption, because flare blast wave theory is mostly rejected by almost all the authors. So could be a failed eruption or maybe still CME, because we only looked say around 4 R0 or so, but then if there is a CME which was not seen below 4 R0, that could also have that could also have been a reason for these type of burst.
Okay, yeah. I mean, of course, if you're looking at 4 solar radii, you can easily miss some CMEs which are very close to the sun, and they have high energies very close to the sun, and within 2-3 solar radii they fizzle out. So maybe that kind of CMEs.
Okay, so that brings us to the end of this session. Shravan, we have some questions. We could put them in this chat here, or you could put them in the Slack channel, so Anshu can answer them. Shravan, over to you.
Thanks everyone, all the speakers. Lovely talks, a very, very interesting session. It is, so we've done a reasonable job. Rajguru, I hope you're happy. We're only 9 minutes over. Yeah, so I hope you enjoy the rest of the conference, and thanks very much for this morning session. Over to you, Rajguru.
Yeah, thanks. Thank you, everyone, and thank you, the speakers, and I thank the session chairs too. So we have about 20 minutes break now. So we will get back at 10:15 Indian time, 10:15 a.m. the next session. Okay, we'll have a short break now.
Can we request the speakers of the next session
Physics 1. Myself, Sampurna from IIA, and Avik Sarkar from PRL will be jointly chairing this session. We have 5 talks in this session. 2 are contributed and 2 invited, and 1 solicited talk. So let us begin the session. So let me first invite our first speaker, Vyacheslav Sadyko from Georgia State University, USA, to deliver his contributed talk on comparison of physical properties of the solar atmosphere and synthetic SDO HMI line of sight observables from 3D radiative MHD simulations. Sadyako, can you please?
Yes. Hello, everyone. Okay, let me start sharing the screen. So, all right, let's share. So, can you see the full screen now?
Yes.
Perfect. Thank you for confirming. All right. Hello, everyone. My name is Slava Sadikov. I'm from Georgia State. And today I will talk about comparison of physical properties which we get from simulations with the synthetic SDO-HMI line of sight observables for 3D radiative MHD simulations. This work is made in collaboration with Irina Kitiashvili, Sasha Kosovichev, and Alan Ray, and we present our preliminary results. First of all, what motivates us? And the motivation is simple, that the insights into the plasma processes in the solar atmosphere come from remote sensing. And correspondingly, it is critical to interpret remote sensing observations to get some information about the processes happening at the solar atmosphere. And such approach was used many, many times in literature. And here are some examples. For example, the Bifrost simulations were used extensively in addition to radiative transfer codes to get physical properties, physical parameters of the atmosphere from the observed magnesium and carbon spectra, and there are many other works. The stellar box simulations developed at Stanford and NASA Ames were combined with spinor radiative transfer code for interpretation of SDO-HMI observables by Irina Kitiashvili previously. The Muran code results were combined, simulations were combined with Multi3D for studying formation of various spectral lines during the solar flare. And we recently made a diagnostics of shocks based on magnesium and carbon spectra, again by combining stellar box and RH1.5D codes. But in this presentation, I'm going to demonstrate some initial results of comparison of physical properties of the solar atmosphere and synthetic SDO-HMI line of sight observables, again by combining stellar box, by combining it with spinor and with our simplified SDO-HMI pipeline. Okay, first of all, the simulations which we consider are done by stellar box code. And stellar box solves the fully compressible MHD equations with radiative transfer, it has a large AD simulation treatment of subgrid turbulent transport. The current version of the code supports the extension to the corona, to the deeper layers, as well as in horizontal directions. And in the bottom here, you can see the initial setup. So we have a domain 6.4 times 6.4 megameters in horizontal direction and 6.2 megameters in depth. And just 1 megameter corresponds to the atmosphere starting from the photosphere. So the grid scale in horizontal direction is 12.5 kilometers, and in vertical direction it varies, but essentially it is of the same scale. The lateral boundary conditions are periodic, and this simulation started with the initial seed feed of 10 milligauss and evolved naturally. And on the right, you can see the visualization of the vertical velocities at 0 kilometers height. So next, for the simulations for which we have about 1 hour of snapshots delivered with 5-second cadence, This modeling is fully done by Irina Kitiashvili. The modeling of iron line, which is observed by SDO HMI, is done using spinner Stopro code, and the computations are done on the column by column basis, assuming LTE with the original spatial resolution and with about 6 million angstrom spectral resolution. The computations of Stokes profiles are done for various projection angles, assuming that we observe the domain at the solar disk center at 30 degrees, 45 degrees, etc. This is the angles here. And we will analyze both the high resolution Stokes profiles and those which are smoothed with SDO HMI point spread function. And by the way, the modeling results for 0, 30, and 60 degree cases are available at NASA's data portal. The link is here, and this is just a visualization of the portal on the right. So everyone essentially can work with this data. And this is the result of the modeling. This is how we scan the across the HMI line. And on the right, you can see how the domain evolves. So how the intensity changes while we scan. Obviously, while going to the center of the line, we see the dimming. We start to probe a bit higher layers with respect to while being at the line continuum. So this is for the initial snapshot considered for this work. All right, so now we have Stokes profiles at each point, and we have them either at high resolution or smoothed. And now we want to model what SDO HMI will see, how the instrument will see this domain. For this, we created a simplified version of the line of sight observables. We have right circular and left circular polarizations used to deduce these observables. And we sample this at 6 wavelengths. And these wavelengths are chosen to be symmetric with respect to the rest wavelength. So the distance between sampled points is here. And we assume that HMI spectral point spread function can be modeled by Gaussian with the following for width of the half maxima. So we don't take care about the side lobes here. The temporal order of scan wavelengths is implemented according to SHOW 2012 in the order in which we scan, and actually full temporal cadence is taken into account. So we really interpolate in between of times to sample the polarization signals. Next, we calculate the Fourier coefficients following Kubida et al. 2016. And you have A and B Fourier coefficients, and that's on the right how you deduce the SDO HMI observables essentially. So what I have to comment here is that you reproduce it obviously to a certain extent. Again, the PSF was modeled by Gaussian. The correction coefficients are applied to line depth and width. In HMI pipeline, the Gaussian width is assumed to be fixed. So we also fixed it fixed it and keep it equal to the median value across the data set. And an important point that we really will not consider here the velocity corrections, but we have results with the velocity corrections applied in our pipeline too. All right, and here are visualizations of the BZ field at 0 kilometers in the photosphere. Next is the BZ observable, which is deduced fully based on SDO HMI pipeline from the Stokes profiles. And the most right is the BZ observable, which is smoothed with SDO HMI resolution, not pixelized yet, and just up to the scale is plus minus 15 Gauss here. So, and you can see how the domain evolves and how the strong fields appears in the intergranular lanes. These fields are up to 1 kilogauss, and how SDO HMI smooths essentially how it observes that amplified fields here. Okay, and next what we try to understand how the velocities the velocity observables are correlated with the actual velocities. For this, we calculated the correlation coefficient between the observables and velocities at each of the height layers and tried to deduce the height which delivers us the maximum correlation coefficient. And on the right, you can see the velocity correlations for 0 degrees. And you can see pretty well that for both. And yeah, I have just to comment that black lines are the correlation coefficients for high resolution for various time moments for various simulation data cubes. Gray lines are with SDO HMI resolution, and correspondingly red and blue lines are the medians of the correlation coefficient across all these lines. So correspondingly, we can see that these correlations indicate a pretty good correspondence of a certain height with the observable, which we observe for 0 degrees as well as for other cases of the projection angles. This is the example for 60 degrees on the right here. So for the magnetic field, it is not so straightforward. Here, for example, you can see for 0 degrees, we see a good correlation for high resolution observables, and the correlations is obviously a bit worse looking for SDO HMI resolution, because the magnetic fields are mostly anyway small on average and deliver a weak signal. So, and actually the situation for magnetic fields is a bit more complicated. For 60 degree case, we still can deduce some sort of an average behavior and average height corresponding to the signal which we see in observables, but the correlations are more ambiguous. So if we consider the average correlation heights, the average maximum correlation heights for the velocities, you will see the following dependence, as you see now on the right figure. So on average, both the high resolution and SDO HMI resolution observables start to correspond to higher heights, obviously, when you move towards the limb, simply because you have more optical depth and you effectively probe a bit higher layers. And the same situation is true for the magnetic fields on average again. And you can see that with the magnetic fields, you probe somewhere between 300 and 600 kilometers if you are at 80 degrees. So effectively for about 200 kilometers higher with respect to solar disk center. An interesting picture is when you start to probe the magnetic fields by applying a certain magnetic field thresholds. For example, you want to probe the magnetic fields only in those regions where the magnetic field was above a certain threshold. And that's the figure which you will see. For 0 degrees, it is not so obvious here, but in fact, it was a decrease here. But for 70 degrees, it is very clear that if you go to the regions with stronger magnetic fields, you start to probe a bit deeper regions, essentially.
Sadhiko, 12 minutes are over. You have 2 more minutes.
Perfect. 2 slides. Okay, and what happens if we try to integrate, for example, the total fluxes or total unsigned magnetic flux in the domain and try to compare what we can deduce from observables? And you can see a kind of summary picture on the right, where we have high resolution observable flux, the high resolution field, the height of the highest correlation coefficient, and the same for SDO HMI. So a general conclusion would be that we underestimate the fluxes when we base our judgment on observables. And the same actually happens with the integrated intensities. So if we base the judgment about the integrated intensities, integrated continuum intensities based on observables, yeah, I believe I was not correct here, we actually overestimate the integrated intensities, which come from the modeling of Stokes profiles simply because of applying the algorithm to deduce that from 6 points. So in general, my conclusions would be the following. So the SDO-HMI velocity and magnetic field measurements are correlated with physical parameters at certain heights of the atmosphere. The heights obviously increase when you move from solar disk center towards the limb, and the deeper layers are probed at regions of higher magnetic fields. The total unsigned magnetic flux, and yeah, that's my mistake. So the total unsigned magnetic flux is underestimated, while the integrated in continuum intensity is overestimated at the solar disk center. So, and in future, we plan certain actions. First of all, we plan to understand the role of the velocity corrections, for example, with respect to the unsigned magnetic flux. We plan to consider unsigned magnetic fluxes and continuum intensities for other projection angles. That was not done yet. And also we plan to compare our simplified SDO-HMI line of sight pipeline with the more realistic one, which was implemented for Irina Kechashvili's simulations of 2015. So by that, I wanted to conclude my talk. Thank you very much for this opportunity.
Okay, questions, Sushant? Can you speak?
Hi, Slava. Nice talk. I really like this work because it kind of models some of the assumptions that go into our data pipelines. But I wanted to ask your results of observing different heights at different locations on the solar disk. Mm-hmm. Do they explain the center to limb effect?
Well, yeah, obviously that should be a part of the center to limb effect. You mean, for example, with respect to sharp properties, or?
In the center to limb effect seen in time distance heat seismology, as well as in local correlation tracking on photometric data.
Oh, I would say we probably didn't test it yet, but probably if you contact Irina, she can give more detail about it.
Okay, awesome, thanks.
Somebody from IIA?
Hi, so this is Rajaguru from the IIA auditorium. Hi, nice work. I just have a question. When you synthesize the spectral line, the HMI line, does your radiative transfer code, it produces the response functions for the different variables, different physical variables, right? Did you kind of check the response function as a function of height and kind of check how it matches with what you see for different observables?
Yeah, that's a very good comment. Unfortunately, we didn't compare the response function or the tau unity heights, for example, for the line with what we correlate with the observables. But as far as I know, the tau unity heights typically for HMI line are about 0 kilometers at the line continuum and about, say, 150, 200 kilometers above for the line center. So the observables of the velocity and magnetic fields are exactly more sensitive to that 100 to 100 kilometer region, which most probably corresponds to the line center formation heights.
Okay, thank you.
Thank you.
Seems like no questions. Thanks, Vyacheslav.
Thank you very much.
Yeah.
Okay, so we will move on to the next talk. The next talk is an invited talk by Matthias Rempel from High Altitude Observatory, USA. He will be speaking about from flux emergence to sunspot structure, a modeling process. I shall remind you after 25 minutes.
Okay, good morning, good evening, depending on where you are. I would like to start thanking the organizers for inviting me to give this review of flux emergence simulations, as well as some recent developments in understanding sunspot structure and sunspot decay. So the general accepted view is that magnetic flux is rising towards the surface from a deep convection zone. Or deep convection zone doesn't necessarily mean it's at the base of the convection zone, and the views have evolved over time, which I will demonstrate in this talk. And this view is mainly supported by the fact that observations show in the early stages of flux emergence strong horizontal expansion of emerging flux, which is a consequence of having a highly stratified convection zone, density contrast of about 10 to the 6. So if flux moves through this highly stratified layer, it has to expand dramatically horizontally. And this has consequences, even if magnetic field starts rather strong somewhere in the convection zone. By the time it reaches the photosphere, it's typically very weak, on the order of a few hundred Gauss. So one challenge is to really understand how this flux is transported through the convection zone in the presence of convection, but then also how the field is re-amplified to the field strengths we typically observe in sunspots. I will start with looking first at the flux emergence in the deeper layers of the convection zone. And I mean here the layers up to about 20 megameters beneath the photosphere. And what's most critical here is for flux bundles or flux tubes, which typically carry the flux of a sunspot. I mean, depending on the field strengths, of course, but they typically have a size which is small compared to a pressure scale height or the typical scale of convection. So they travel several times the diameter, and what's critical is interaction with ambient flows, which also includes the flows created by the flux emergence itself. And this has been modeled over the past 20 or even 30 years through several approaches, going from thin flux tube approximation to anelastic MHD models. So I start with here an overview of some of the older results, which were based on the thin flux tube approximation. And in these early simulations, properties of sunspots were explained through these thin flux tubes rising to the photosphere. During the rise, the Coriolis force causes the tilt angle of sunspots, but also asymmetries between leading and following spots due to flows along the rising flux tube. And many of these aspects also have been seen in more recent 3D anelastic simulations. Here's an example of a simulation conducted by Yong Fan in 2008. Now, one outcome of all these models was that they work best if these flux tubes have initially 100 kilogauss. This was consistent with stability considerations in the overshoot region, and this is required for having low latitude. Recognized in 2D simulations that these flux tubes will break apart when they rise through the convection zone. So it was then found that using twisted flux tubes, one can concentrate more flux in the rising flux tube. And this is an example of such a simulation. In the twisted case, more flux remains concentrated in the head. But the addition of this twist had some unwanted consequences. The amount of twist was typically almost an order of magnitude larger than what is observed in sunspots. So the twist influences the tilt angle of sunspots. And if one uses a sign of twist, which is observed in sunspots, the tilt turned also the wrong way. So this was kind of a trade-off between stability and the resulting tilt. The problem was less severe in 3D setups. Now, the other challenge of these early models was the field strength. 100 kilogauss is more than 10 times the equipartition field strength. This is really difficult to achieve. And there were other processes proposed, like the explosion of flux tubes, where potential energy is converted. Another challenge was also addressing the past emergence evolution. Typically, these flux tubes had m equal 1 or 2 instabilities, so the flux loop had in the end legs near the apex, which were almost parallel to the surface of the sun. So once such a flux tube would break through the surface, you would get a very rapid separation of the polarities, which is not observed. And one possible way this has been addressed was the picture of dynamical disconnection, which is actually related to this explosion of flux tubes I mentioned earlier. Now the field moved on, and one critical addition was the inclusion of convection in these simulations. This was addressed in 2 ways: full 3D anelastic MHD simulations. Well, they have the challenges difficult to get enough resolution to really resolve a flux tube which carries something like the typical flux of a sunspot of 10 to the 22 Maxwell. So these simulations had rather thick flux tubes. But there has been also a very interesting approach by Weber, Fenn, and Misch in 2011 and follow-up papers, where they essentially stayed with the thin flux tube approximation, but embedded the flux tube in the convective envelope of a 3D convection simulation and coupled the flux tube with these convective flows. And in this model, it was then found that actually the rise of flux tubes is mainly dominated by convective timescales, and the results were much less dependent on the initial field strength, and actually the best agreement with observation was found for field strengths more in the 40 to 50 kilogauss range. It was also found that, I mean, flux emergence, there's a lot of failed flux emergence where you have kind of loops forming, but they don't make it because they were hit by a downflow. Only if the conditions are right and one of these omega loops is embedded in a consistent upflow, they're actually transported towards the surface. But you also see is kind of the wave number of these loops is now a little bit higher. So it's not the m=1 or m=2 instability, which is more consistent with what would need for the post-emergence evolution of the resulting sunspots. Now I move on to simulations of flux emergence in the upper convection zone. The perhaps most significant difference is really that once you get close to the photosphere, the flux bundles, which carry the flux of a typical sunspots, they have a size which is larger than a pressure scale height, a typical scale of convection. So you do have a situation where these flux bundles travel at best about their own diameter, but at the same time the density drops by a factor of 10 to the 4. So the dynamics is heavily influenced by horizontal expansion and the resulting weakening of the field as the emergence progresses. And in order to capture this, you need fully compressible MHD. And if you want to add a realistic photosphere, then you also have to add radiative transfer in these simulations. Now, many of these simulations were considered in separation from the deep convection zone. So flux emergence has to be initiated. And there are about 4 different ways to do this. One quite common way is that a buoyant flux tube is inserted in a convection domain and then rises and is transported by the present convection. Another way is the advection of horizontal flux in upflow regions at the bottom boundary, an approach which was first done by Bob Stein and Åke Nordlund. Kinetic advection of a half torus of flux or other shaped flux bundles at the bottom boundary has been early on used mostly for emergence in the corona, but this approach also has been adapted for studying sunspot formation by Mark Jung about 10 years ago. And the more recent way is the one-way coupling of a 3D dynamo simulation to such a surface flux transport model. This is an example from the simulations conducted by Bob Stein and Åke Nordlund, where they just imposed a horizontal field of about 1 kilogauss at the bottom boundary. What is really interesting about the setup is that the scale is naturally selected by the convection present in the domain. You don't have to impose a certain scale. Now, this is a simulation domain which isn't too large, which is 25 megameters wide. So you end up with something like ephemeral active regions. This emergence is completely passive. It's dominated just by the convection which is present in the simulation domain. And in principle, these sort of setups could be scaled up to actually form larger size flux concentrations as well. Now, this is an example from the approach of imposing an emerging half torus at the bottom boundary. Now, here one has much more control about what is pushed into the domain and at what speed. These simulations it's easier to reach an active region scale in terms of size and flux. And for example, one can also explore the effect of a field-aligned flow, which is expected to emerge in some of these simulations which start deep in the convection zone. Now, what these simulations really show is, what is critical is that the magnetic field is during this flux emergence process effectively decoupled from the mass which is embedded in this magnetic field. And this requires that the field becomes very weak and you form small scale loops which essentially shed a lot of the extra mass to reconnection. And when the sunspots form in these simulations from the weak field, the flux transport is dominated by a turbulent EMF. So you actually can form a sunspot in the region where you have divergent mean flows because it's the turbulent EMF which does transport the flux together. And when this movie perhaps repeated one more time, essentially, and you see this nicely here in the leading spot when that is forming, that you actually have an indication that there's a top-down formation of the sunspot. You first transport a lot of weak field in the photosphere. You see a top-down formation of a stronger field, and this field collapses in a region where at the same time the mean flows still show outflows. Now, this simulation also had a field-aligned flow, which leads to the asymmetry. And this was similar to what is expected from these thin flux of simulations, that you have a retrograde flow. And this actually leads to a situation where the trailing spot is forming earlier, which is not what the sun is doing. And it's actually the case that these retrograde flows have not been found in observations. Now, this is perhaps one of the most critical observational constraints, which has been there recently for flux emergence. This is a helioseismic study. This is an observation of about 100 active regions. And in particular, what was studied here is flows in the 24 hours before flux emergence in the photosphere happened. And what was found is that in the helioseismic data, there is not really any indication of consistent upflows, retrograde flows, or any of these flows one would have expected from an active flux emergence. The panel here on the right shows actually simulation results, and depending on how fast you move flux in at the bottom boundary, you can create quite dominant horizontal outflows, which should be easily visible in helioseismic data. But what it turns out is the only simulation which is kind of consistent with the observations, which kind of is in this error bar introduced here by the observations, is this one case where the emergence speed was essentially comparable to the typical convective upflow speed at the bottom of the domain here in 20 megameter steps. So the big takeaway from these constraints is really that the flux emergence in the uppermost 20 megameters of the convection zone is mostly a passive process. Now, the next big improvement in recent years was that some of the global dynamo simulations were capable of producing flux bundles in the convection zone of a couple 10 kilogauss. And these flux bundles rise when the conditions are right towards the top boundary of the simulation domain and form kind of these short omega loops. But these are not really flux tubes. The feed lines are pretty ergodic when you move away from the flux concentration. And these flux bundles are mostly transported to the surface by a combination of the convection present and some buoyancy effects. But also was found in these simulations, actually these flux bundles do have a prograde flow because they are associated with these banana cells, these larger scale convection cells, which are influenced by rotation. And these cells, they are also the ones which actually produce these flux bundles in the first place. So it's not the mean differential rotation which really builds these flux bundles, it's more the non-azimuthal components of the zonal flow. Now, interesting question, which is arising, of course, from these simulations is, do these flux bundles, would they actually form sunspots if we could continue the rise all the way into the photosphere? And this was achieved by actually coupling one of these dynamo simulations to a surface simulation. This is work by Feng Chen a couple of years ago, where he used the Muram code. And he used one of these flux bundles created in Yu Hang's global dynamo simulations was imposed as bottom boundary. Now, the great advantage of doing this is that you impose at the bottom boundary magnetic field and the flow field which are consistent with each other, because this is the flow field which brought the flux up towards the surface in the global dynamo simulation. And it was found that you form an active region out of this. The leading polarities were forming first and they're stronger and more coherent, which has to do with this effect since there is a prograde flow in these emerging flux bundle. Most of the leading flux is essentially pushed into this consistent downflow lane at the leading edge, whereas the trailing polarities are more found above upflow regions. Now, perhaps some of the most impressive simulations which have been recently conducted are these simulations by the Japanese group, Hideyuki Hotta, Shin Toyomi, and Iima-san. They were the first ones who were able to actually conduct radiation MHD simulations in a domain which goes all the way from the bottom of the convection zone into the photosphere and then a couple 100 kilometers above. So you end up with a mean density stratification of something like 10 to the 9 to 10 to the 4. This is an example where they did start from a horizontal flux tube, which was originally inserted. This was a twisted flux tube, which is then brought into the photosphere by the convective flows. The twist led, in this particular case, to rotating spots, which then created a delta spot, which had these very strong light bridge with very strong horizontal feed of up to 7 kilogauss, which also has been found in Hinode observations. Now, these simulations indicate that likely whole convection zone simulation are really in reach, and that is likely the next step which will be undertaken. But this is also a big challenge, since once you really get to these really large scales, there are some challenges in our understanding of large scale convection. So this is more complicated than just scaling up a domain and pressing the return button on a big computer. And we will hear more about these challenges, I think, in some talks later today. Now I would like to talk a little bit more about the structure of sunspots and penumbra and sunspot decay. Now, there have been in the past many sunspot simulations which have pretty sunspots with a nice penumbra, but one thing I really would like to discuss here is the one thing we still don't really understand. And this is, I mean, how do you form a penumbra in a self-consistent manner? What I show here in this movie, this is a simulation which circles through two different top boundary conditions, which differ in terms of the inclination angle of the field. If you do impose a sufficiently horizontal field, you do get a penumbra, but if you switch back to a potential field, the penumbra actually disappears. And this has been pretty much the state of affairs for the last 10 years. And there are a lot of things people discussed. I mean, perhaps one interesting one was this one, that there is actually a chromospheric precursor visible before penumbra forms. So there was maybe some idea, maybe this more strongly inclined horizontal field is something which happens on the sun. But I will show on the next slide some indication that this is not the case. The perhaps most interesting new direction is what was first suggested by Orkan a couple years ago, that perhaps it's really the subsurface structure we still don't get right in these simulations, that you may be able to get a more extended penumbra if you have a more concentrated foot point. So first talking about this top boundary issue, and is there any indication that there might be a stronger horizontal field or something like this happening on the sun? So in recent observations, it was found that the umbra-penumbra boundary is actually given by a critical field strength of about 1,800 Gauss for the vertical field. And this seems to be pretty constant across different sunspots of all types of different sizes and shapes. Now, if you look in simulations, and I show here a couple of simulations which have been analyzed, is if you actually use these simulations which impose a strong horizontal field, while they have a nice penumbra, the feed strength is actually too weak at the umbra-penumbra boundary. Only if you have a potential feed, you get more close to what observations have, but you're still falling a little bit short. Also should mention that it has been discussed that actually this existence of a critical feed strength may be related to the Guth-Taylor criterion, which was derived in 1966, which is a modification of the Schwarzschild criterion for convective instability modified by the presence of vertical field. Actually, vertical field has a stabilizing effect, which might indicate this sharp transition between the umbra and penumbra boundary. And this is currently further investigated by looking into sunspot models. Now, looking further at the subsurface structure, there have been recently this in the investigation by Panya et al., where they looked at the role of the fluting instability, essentially setting up different subsurface structures with different concentration of the foot point, different curvature, and you can create subsurface magnetic field structures which are heavily fluting and unstable. And what they could demonstrate is that this fluting instability can help to promote penumbra formation, but also it's also critical that you don't get too much fluting, because you also can easily stabilize the sunspot, which has happened in this case. Now, typically these sunspots are more stable if you go deeper, but this is certainly an indication that the subsurface structure is something which has to be investigated more carefully. Now, talking about fluting, that is also interesting in conjunction with sunspot decay. This is one simulation I ran a couple of years ago because I actually wanted to study how a sunspot decays. Now, this sunspot decided in the end not to decay, and I gave up after 100 hours, but still I think we learned a couple very interesting things about sunspot stability from it. So what I show you in the top panel is the flux content of the sunspot. When there was a penumbra present, it was pretty much steady over at least here the last 80 hours of the simulation. When I removed the penumbra in the simulation, which was done through the top boundary condition, the sunspot actually was decaying. Now you could see in the movie there were some indications of kind of fingers entering the umbra, which suggests that some fluting is happening beneath the surface. And this was recently investigated by Hannah Strecker. She analyzed the stability of the sunspot and found that it's heavy fluting and unstable, roughly in a depth of 3 megameters. Above that, the penumbra has a stabilizing effect, which is along the lines of what was already discussed by Meyer et al. In 1977. Now, the sunspot, the core of the sunspot really becomes heavily corrugated and is close to be falling apart. But nonetheless, the flux, the sunspot does not really decay in terms of the photospheric flux, because the mode flow which developed around the sunspot has a stabilizing effect. Having a mode flow means that there is a strong upflow underneath the penumbra, and this one prevents the submergence of field. So the sunspot is in the strange position where it actually, the core of the sunspot decays, but the flux cannot escape. And this escape can only happen when the penumbra disappears, which in this case was simply done by changing the top boundary condition. Okay, that brings me to the summary of this talk. I mean, I hope I can convince you that a lot of things has happened in this field. And most importantly, that there has been quite a paradigm change in understanding of flux emergence from a rather active process more than 20, 30 years ago, where people thought it was really strong flux tubes rising towards the surface. And in more recent years, it's really more a passive convective process, where it's mostly that the convective flows which are present there all the time transport flux into the photosphere. The future is likely that these simulations will be extended in scale, going really to whole convection zone flux emergence and dynamo simulations. Penumbra formation is still a big mystery, but there's some light on the horizon. But it's still very puzzling that it appears at least that the sun gets this process right almost all the time. You don't see too many failed sunspots. But in simulations so far, we find a penumbra only if the right conditions are chosen in the setups, either through boundary conditions or subsurface structure. Thank you very much.
Thanks, Matthias. Question from Sushant.
Hi, Matthias. This is really nice. I learned a lot from this. But my question is about the simulations in which you were studying sunspot decay. You talked about mode sail flow beneath the penumbra, but do you see the kind of inflows around that sunspot as are seen on the photosphere through helioseismic studies?
So when you talk about inflows, I mean, do you mean on larger scales? Because if you're really focusing in the area around the sunspot, you have first the evershed flow with an outflow, and then you have the mode flow, which extends by another 10 megameters. No, the mode flow is not really a continuation of the evershed flow, at least not in the simulations. But at least on that scale, you see a dominance of outflows. So are you talking about the inflows which are seen on even larger scales, or?
Yeah, but the inflows are seen from within 2.5 degrees from the active region to like extending to more than 10 degrees. Right?
Yeah,
so,
I mean, this is much larger than what is captured by these simulations so far. So,
okay,
I mean,
so you expect there to be outflows really close and then the inflows dominate farther?
Yeah, I mean, at least to me, the mechanism which has been proposed is likely that you have in active regions, in the active region belt, typically enhanced radiative loss due to all the small scale magnetic elements. And that might cause a larger scale, very small pressure imbalance, which does drive flows converging towards the active region belt. And this is along the lines of what Hank Sprout suggested as driver for the torsion oscillations, at least for the low latitude branch. But this is really on a scale which we cannot model right now in these simulations. I mean, one would have to extend them quite dramatically and then run them for long enough for these very weak radiation effects really to likely have an influence.
Thank you.
Dipendu?
Yeah, Matthias, thank you for a great talk and good to see you. I have a question, maybe a doubt here. So the interpretation that the near surface dynamics is passive implies that some of the properties that the active region, emerged active region shows in the solar surface is governed by the near surface flows, as you said. If this is the case, how can this be reconciled with the general understanding that the observed tilt and twist, which sort of global features of an active region, are a consequence of dynamic interactions throughout the rise process?
So, I mean, that it's passive does not mean that all the history of what happened to the rise is erased. It just convection will add a random element to it. But I mean, you still have some, if there is some large scale symmetry present in form of a tilt, some asymmetry in field strength, I mean, some of this survives. But I mean, you're touching here a really interesting question, because in particular, the question of tilt, I mean, there have been recent studies which suggest, at least in the early stages of flux emergence, you don't really see a preference for tilt that establishes during later phases. And it might be that Hannah Schunker in her talk later today or tomorrow might actually touch on some of these recent observations. So I think, yeah, this issue is not completely settled. To which degree, for example, the tilt is really due to deeper seated dynamics, which now in these passive simulations, it could be simply the helicity with the kinetic helicity present in convective flows, which bring actually the flux into the photosphere. They will impose a tilt angle too. I mean, in addition to the Coriolis force acting on the flows of a buoyant rise flux tube. But it might be also simply the Coriolis force acting on the sunspots as they separate from the emergence side could also add additional tilt to it. I think this is still an open question, really, which process adds too much here.
Right, thanks.
Okay, if there is no more question, may I ask Vyacheslav to check the chat box? There is a question for you, and then we'll move on.
Okay, thank you, Matthias, for a very interesting talk. We will now move on to the next speaker, Renya Trampedok from Space Science Institute, Boulder, USA. He will be presenting the invited talk on 3D simulations of convection and why. Renya, can you please go ahead?
Yeah.
We'll find you after 25 minutes.
Can you all see it?
Yes.
Oh. Okay. First, I'd like to thank the organizers very much for giving me this opportunity to present this review. It is going to be without any animations of convection, actually, because I'm going to show a little more about kind of integrated quantities that we can extract from simulations that can be useful for all kinds of things. But first, I want to show this comparison here between simulation and observations. They're not made to be directly comparable, but it shows we're doing not too badly. Okay, first a little about types of simulations. One dichotomy is between local, like box in a star simulations, where you have a little box of simulation domain sitting typically in the surface layers of stars, and then the global simulations, where you either have a spherical, typically a spectral simulation, or you have a, like shown by Augustin there, or you have a star in a box simulation, shown in the case of Betelgeuse by Bernd Freytag there. And then, of course, there are all kinds of other things that you can distinguish different simulations, whether they are magnetic fields, what kind of time stepping, type of artificial diffusion, atomic physics, radiated transfer methods, and all these kinds of things. But a basic dichotomy is if they're local or global. So to get a feeling for that, the difference between the two, let's have a quick trip here through dynamic scales. That was a typical local simulation. And then in the background here, we have a supergranulation simulation, which is 96 megameters on the side, 20 megameters deep. And that goes into a spherical segment simulation by Kyle Augustin. And then it goes into the half cross-section of an ash simulation by Mark Misch et al. From 2008. And you can still see the original little simulation, local simulation up here. It's just a few pixels wide. So that's the range of scales that we're looking at. And the big problem, of course, is that all the small scales and all the fast-moving stuff is happening at the very surface, which means if we want to make a full sun simulation, you would have a very large area that you had to cover with very high cadence and very high resolution. But we also see that you have coherent structures that span the convection zone here. Okay, so local simulations include the observable surface, which is good because that's where we get the photons that we study. And we also have the majority of the excitation and damping of P modes. So if we want to do seismology, that's a very important part of the star. And it's also where the entropy jump is set up at the top of the convection zone, which determines the adiabat that the whole convection zone lives on. And the surface region is also where you have the highest amplitude, highest Mach number convection, and hence what's furthest away from what you can treat in perturbation calculations. Global simulations, on the other hand, include the interactions between rotation and convection, which sets up global flows like meridional circulation and differential rotation. And they also include, oftentimes at least, the overshooting below the convection zone, and can shed light on what additional mixing processes are, like shear from differential rotation and G modes and stuff like that. And they're very much complementary, the two kinds of simulations. But what do we need all these 3D simulations for? Matthias just showed that they can be very useful for sunspot analysis. So I will not cover that at all. I'll cover a different set of things here. So first of all, you can improve your stellar structure and evolution models by things like mixing length calibration, so the photospheric transition described by Titor relations. And maybe you can find a way to include turbulent pressure in your 1D models. You can also improve helioseismic modeling. There's astroseismic surface effect, which is a shift in frequencies caused by stuff happening very close to the surface. So that we need local simulation for. And there's also the mode excitation and damping happening. 3D simulations are also very useful for improved spectral synthesis and abundance analysis, where the correlations between velocity and intensity gives actual observed profiles without any free parameters to adjust, like micro and macro turbulence or mixing length parameters. Then we can also use them for limb darkening, for transit, calculations of transit profiles, and for interpreting interferometry. This is, of course, most interesting for stars other than the sun, where we can't observe it directly. But we can compare between the direct observations of the sun and the simulations to see if our simulations get things fairly right. And then we can go on to study transits by planets, for example, in front of other stars. And also in general, we can get an improved understanding of what convection actually is, the morphology of it, and the basic ideas of how it behaves, which will enable more realistic models. Okay, so I'll start with what we can do to improve solar structure based on these simulations. So one issue is outer boundary conditions of still models. It's a very thin layer, but it does determine the adiabat of the convection zone, which means it affects the overall structure of the star. This surface layer has three components: the atmospheric opacity and the optical transition in the photosphere between optically thick and optically thin. And this you have to run full atmosphere modeling in order to figure out this transition. That means solving radiative transfer for hundreds of thousands of wavelengths. And then there's the efficiency of convection, as measured by, for example, the mixing length parameter alpha. And bear in mind there are at least three other parameters in the mixing length theory that in principle all need to be calibrated. Okay, the photospheric transition via Titov relations. So using Titov relations is using the full radiative transfer solution of an atmosphere model in a 1D model without having to go through this very complicated calculation, time-consuming. So you calculate an atmosphere, and then you make a grid of those atmospheres so that you can interpolate them in for the still structure model. And we reduce the Titov relations to the Hopf functions as shown here below. So here we have in black solid, that's a full Titov relation of the simulation, and the magenta is a Marx model. And you can see very clearly that they have a different transition to convection here. The dashed lines here, on the other hand, are the temperature structure reduced to a completely radiative one. So they converge to something very similar, but they're still different out here in the photosphere and above. So these two plots here shows the Hopf function, so reduced Titov relations. So I guess I didn't mention that tau is optical depth. The right-hand plot has curves separated, and it's a log G sequence going from the main sequence up to giants at 5,000 Kelvin effective temperature. And you can see in the left side plot that the green dashed lines, which show the 1D Marx atmospheres, they're very much the same, all of them, but the simulation shows a lot more difference in behavior. And in particular, the level of the Hopf function at the top here actually has an effect. The optically deep convergence here has an effect on the model. In comparison, the dotted line here is gray atmosphere. So real stellar atmospheres are very far from gray. With those Titov relations as boundary conditions, we can now carry out calibrations of the mixing length. And here I show examples, first one by Hans-Günter Ludwig and collaborators, and then myself. Oh, there should have been a plus there. I didn't do this myself. We were a team. And Sasral Magic a year later here. So they all show fairly similar things, that there's a plateau around the sun and increasing mixing length towards cooler stars and decreasing towards warmer stars. Okay, helioseismic modeling. All simulations have waves in them. The initial state that you start your simulation in will not be natural state of simulation, which means it'll have excess in energy, which goes into modes. So normally during the relaxation of a simulation, you'd like to dampen these modes so you don't have unnaturally high mode amplitude. And you'll have these modes even if you have minimal actual excitation and damping in your simulation, like in the global simulations. Local surface simulations of convection include most of the excitation and damping, which means you have amplitudes that are physically real for the simulation. And if your simulation is realistic, they should be very comparable to actual physical reality. But you don't include the full acoustic cavity, which means you have too low a mode mass, which means you get high amplitude. And also you only have very few modes. So all the energy is going only into these few modes because they're constrained by the size of the parts. Global simulations, on the other hand, are quite the opposite of exactly the opposite of local simulations. You have all the modes, you have the correct mode mass, but because you don't include the very surface layers, you don't have the critical part of the excitation and damping in the simulations. So here, just to show that we have modes in simulations, in the left-hand plot here is a plot of modes in Stein and Norland simulations of a super granulation sized box at the surface, nice P modes. And then on the right, we have a G-mode diagram by Alvan et al. From 2014 for an ash simulation. And then below we have what actually happens in the sun, the P mode spectrum. And the seismic surface effect, it's illustrated in the plot here, where we see the frequency differences between modes as function of frequency between modes in the actual sun and a model of the sun, a normal 1D model of the sun. So the solar modes have lower frequency. And this, the shape of it, that's only dependent on frequency, means that it's due to stuff happening in the surface layers. And there are two components. There's the structural part, which is the difference in the stratification of the atmosphere. Realistic 3D convection simulations have expanded atmospheres compared to 1D calculations. That's partly due to turbulent pressure and partly due to a phenomenon called convective backwarming, which both of them mean larger acoustic cavity and hence lower frequencies. Oops, sorry. And then there's also the modal part, which is the direct interactions between modes and convection, which includes all of the non-adiabatic effects like excitation and damping, and also leads to to frequency shifts. Here's an illustration of the structural part of the surface effect. This is a pressure plot near the surface layers as a function of depth, and this temperature plot. And the dashed magenta is a 1D model, and the full solid black is average simulation. And they've been, the 1D model has been calibrated to match at the vertical dashed line here. And you see the difference between these two dotted vertical lines shows you the expansion of the atmosphere. which causes a larger acoustic cavity. And the effect of this expansion gives you this change in frequency, where you have the frequency shift divided by the nu max, the frequency at the middle of the peak of P modes. And you have small effect, fractional effect at main sequence cool stars, and you have the largest effect for giants. Here in this atmospheric HR diagram, where you have effective temperature and log gravity. The model part of the seismic surface effect was explored here on the left by Hudek et al., where they used 3D simulations to calibrate various quantities needed by a 1D non-adiabatic mode calculation. And they reproduced the actual observed surface effect very nicely. And here is another approach by Skov and Birch in 2020, last year, where they ran a number of simulations with different depths in order to get different modes in the simulation, so they could explore the spectrum here. And they found also seismic surface effects that match very well with observations. You can also get damping rates of the modes. You can measure the width of the excited modes in the simulation. And this is shown here. This was a study by Yixiao Zhu, and he ran simulations that he forced, where he forced at an oscillation at the bottom boundary to then explore the whole spectrum here. So each triangle here is one simulation with a mode that was forced at the bottom boundary, and matches fairly well with black pluses here, which is observed line width in the sun. The global simulations can be used for studying G modes, and as they're excited by overshooting, as shown here for Alvan et al.'s simulation, ASH simulation. And here we see a spectrum, the spectrum of modes, and a number of eigenfunctions there. The eigenfunctions of the simulation compared to those from Adipol's calculation. Improving spectral abundance analysis. Some of you might be aware that there's an abundance controversy that was sparked by spectral abundance analysis on a 3D simulation some years back, started by Martin Asplund and collaborators. So this is quite important. So the main point about doing spectral analysis on 3D simulations is that you get rid of all these fairly free parameters of micro and macro turbulence and the mixing length and the additional auxiliary convective parameters that are actual part of the mixing length theory. And also that asymmetric line profiles emerged naturally from these convective velocity intensity correlations. And that means the profiles are predictive. So you can actually find blends that were previously hidden. So this example of such a blend. So it was known that there was a nickel blend in this forbidden oxygen line, but it was not quite known how large an effect it had. But in the symmetric profiles of the simulations, it was quite clear where it was because you could subtract the oxygen line and you saw the bump. In 1D, if you just look at the line there, you can't see it. It's very well hidden. And with since 1D calculations don't give you the actual asymmetry of the line, the curved bisector, you can't really tell. So here's an example of recent non-LTE hydrogen line calculation by Anish Amasi. And we should see the very good fit to the three first in the Balmer series, alpha, beta, and gamma. And we see that they match very well. You can see that best in the bottom panel showing the residual. So all three lines can be matched with the same underlying atmosphere. And then in the bottom right-hand plot here, show a comparison of different kinds of calculations there. In the bottom panel of the residuals, you can see the difference between LTE and non-LTE as a dashed black line for 3D calculations, and then two 1D non-LTE. Yeah? Ooh, we're getting close, yeah. And here are a couple of examples of line profiles from simulations by Cafao and Pereira and Scott. Two top oxygen lines, chromium-2 lines, just for example. They're reproduced very, very well. And Martin Asplund's iron line paper shows the bisectors are very well reproduced in the bottom right. Limb darkening. So that's how the intensity goes down towards the limb. And there's some inherent 3D effects that you can't include in 1D calculations here. You can see from this plot. And some limb darkening calculations work very well with 3D. Here's a comparison of 3D and 1D, and here interferometric observations of alpha Cen B. Yeah, synthetic transit calculations showing you the granulation scatter in the profile. And here difference between 1D and 3D calculations, 3D solid dashed, and summary. So realistic 3D simulations of convection provide crucial new elements to the interpretation of stellar observations, and many of them cannot even be asked in 1D with 1D models. One simulation cannot yet cover the whole sun, so simulation type will depend on the purpose of the study, the kind of question you want to ask. But of course, look out for the Synergy European Research Council project, Whole Sun, and a few other projects that are aiming for whole sun simulations. And that ends my presentation. Thank you.
Thanks, Regner. Somebody from IIA, I think Rajaguru.
Hello, myself Shahil from IIA. I want to ask one question regarding this global and local convective simulations. So you mentioned about this for the local simulations, we can't have many modes because of this length constraint, right?
Yeah.
So can you say something regarding this horizontal scales of these simulations? So if I do in horizontal scales, in terms of if I do a square if I take a square box or a rectangular box where this length is much larger than the breadth, so how results can be different for this rectangular box or this square box? Can you say something on that?
Well, the horizontal size gives you the possible horizontal wave numbers, right?
Right.
And so you're asking if they have two different sizes in the horizontal dimensions?
Yes, yes.
So presumably you can have, you have other wave numbers available for the X direction compared to the Y direction.
Okay.
That might be an interesting way of increasing the number of available modes, actually.
Okay, okay. So, so both type of simulation, you think that they can excite many modes. So in terms of this square or rectangular domain, horizontal domain.
Sorry, I didn't hear the very beginning of your question.
So if I just compare in terms of modes, so this square and this rectangular simulation box can both excite those modes. There is no preference in this horizontal direction size or the ratio between this length and breadth.
The energy just goes into the modes that are available.
Right.
It's that simple. So you have the same amount of excitation as function of depth in the simulation, and then you just convolve that with the mode amplitude of the modes that are available. But the depth, of course, is very constraining on what radial wave functions you have available.
Okay, thank you.
No, please.
Okay, you made some comments about modeling G modes through these simulations, and G modes are supposed to be evanescent in the convection zone. So if the G modes have to be excited, have to exist in the sun, then they have to be excited by some process below the bottom of the convection zone, presumably. So do your simulations throw some lights? Or what is the mechanism by which G modes may be excited? And if there is any possibility of ever observing them at the solar surface?
No, my simulations don't. I don't run these simulations. I run the local surface simulation. But these ASH simulations do shed light on that. And in this plot here, they actually show the excitation mechanism of the little insert here shows how a plume from the convection zone smashing into the bottom of the convection zone excites the mode. And if we look here at the eigenfunctions of these three particular modes, you can see how they're all evanescent in the convection zone. And they're only oscillatory inside the convection zone. So these simulations can tell you about the excitation mechanism and also how efficient it is. But there's some limitations on, you need very high resolution of the interface between the convection zone and the interior, radiative interior, in order to have a high level of confidence in these results, because they're very, if you have large artificial diffusion, it will diminish the excitation. So I'm not sure we can actually say something quantitative about how observable these modes should be at the surface. But you can get some upper limits, I guess.
Okay, thank you.
But these phenomena are also very important for mixing processes inside the sun, by the way, even if we can't measure them at the surface. Thanks.
Oscar, can you quickly ask the question? We are running out of time.
Okay, yes. Good morning. This is Oscar Schneider. I just want to quickly to know what is the status now of this controversy in abundancy determination that you mentioned. Is that still existent or has this been resolved?
it has not been resolved. Still working on it. And I'm actually working on a complementary side of the issue, which is interior opacities. I'm working on a new equation of state for whole stars, which includes both what's covered by the simulations, but also the deep interior of the sun. And the new abundances, of course, caused much lower opacity at the bottom of the solar convection zone. And we are having some confidence that these new calculations with both new equation of state and new opacity calculations will actually give higher opacities. Whether it will solve the problems, that remains to be seen, but work is in progress.
Okay, thank you.
Thank you, Ragnar. So we'll go on for the next talk.
Thank you, Renia, for an interesting talk. We will now move on to our next speaker, Nishant Singh from Ayuka, Pune. He will be presenting his solicited talk on self-consistent formation of sunspot-like magnetic flux concentrations. Nishant, please go ahead. I'll remind you after 12 minutes.
Hello, can you all hear me?
Yes. Yeah.
And can you also see my slides?
Yeah, you can put it in the presentation.
Yes.
Perfect.
Yeah. So thanks everyone for joining, and thanks the organizers for this opportunity. I also would like to thank Matthias Rempel for a very nice summary of relevant previous works and also many of his works on the topic of the sunspot formation. I will be basically highlighting some of the things Matthias has already mentioned, and also pleased to hear that our understanding has evolved, as we also will see in these examples, that from the more active emergence to more passive emergence, which is exactly what we observe also in these simulations of the top layer convections of the sun. This work is done with Petri and Marit using the pencil code. Some of you might have seen these in very recent ASI meeting, so apologies to those. But to entertain the rest, I will still show these, that the story of cosmic magnetic fields starts with the sunspot. These are some very beautiful sketches. I at least like them very much. Very early sketches by Christoph Scheiner from 1630. And you can take a look at a variety of many such drawings from this book, Rosa Ursina. And the modern sunspot looks more like this, which is very close to the drawn ones in Christoph Scheiner's drawings. So and as Matthias has highlighted, there is a lot to understand still, and the paradigm is continuously evolving about what is the mechanism that is forming the sunspot. And so long as we keep doubting our current understanding, I think there is a great hope in even very recent future, I think. As we know that the sun shows this global cyclic dynamo, and a number of works, different groups, codes, and physics, they routinely produce solar-like cyclic solutions. And these are basically the global solutions, global magnetic fields, which show a butterfly-like pattern. And the question remains that although these are the diffuse large-scale fields present in the sun, none of these actually form the sunspot or the concentrations. And one reason I put in the title self-consistent is the reason is that we, in our simulations, do not want to impose any strong magnetic field in the domain, simply because our understanding of the dynamo or the large scale dynamo is that it saturates at not very strong levels. It saturates at sub-equipartition levels. And therefore, in these simulations, we will be imposing a very weak uniform field. So the setup is more like this. And some of you might be already familiar with Petrie's earlier work. So these are like Cartesian domain with setup for turbulent magnetoconvection. Usual MHD equations are there. And Rayleigh number is large. So there is a turbulent convection. These simulations that I'm going to show very quickly in the interest of time is that these are the large eddy simulations where not only the viscosity, but also the magnetic diffusivity is of Smagorinsky type. These were performed on the Price machine in Spain. For some couple of these simulations, some 40 million CPU hours were used. 1024 cube simulations on some 4,000 cores using the pencil code. And it's a setup. This box is basically as an aside to motivate why we don't impose a strong field, but the rest is simply showing the background state. As Matthias has already highlighted, that the density drops very significantly close to the surface. And this is the domain of 100 megameter by 100 megameter by 25 megameter deep. So horizontal extents are 100 by 100 megameter and the depth is 25 megameter. We do capture the very surface here and the density contrast in the simulations is on the order of 3000. And these, as you know, are very close to adiabatic stratification. So density and scale heights are evolving like this as a function of height. And very close to the surface, the scale height drops very significantly. And that's where the resolution, resolving these scales become very important because much of the dynamics is governed by these very near surface flows or the near surface convection. Resolution in these simulations will be 0.09 close to 0.1 megameter in the horizontal extent. But for the vertical one, we, although the domain is 4 times smaller, we have kept the same number of grid points to resolve the top layers so that one has at least half a dozen to close to a dozen grid points per scale height. That was important. So we also additionally impose towards the bottom. This is the bottom here, and this is the top. In other units, this is the bottom, and 1 is the top of the domain, unscaled here, sorry. And this is the strength of the horizontally lying uniform magnetic field, non-uniform, in the sense that this is concentrated towards the bottom of the domain. So on the order of about 5 to 30%, that's the field strength that we impose, at most 30% of the equipartition strength. This is already normalized. So, and the reason for that is that the dynamo is typically saturating at very sub-equipartition levels. Suppose there is an alpha effect, which is what was the hint to us from these observational studies. If you're interested, you can look up this paper, that if there is an alpha effect working in the sun, one does expect the solar magnetic fields to be bihelical because the net magnetic helicity cannot be generated. And therefore, the magnetic field should have opposite signs of helicity at large and the small scales. This is indeed was observed for the solar cycle 24, that if you look at the sign of magnetic helicity at large length scale, small wave number, these are the wave number. This is basically the magnetic and helicity spectrum, magnetic helicity spectrum of the sun as a function of wave number. These are the large length scale where you have positive magnetic helicity, exactly as you would expect from an alpha dynamo. This is the expected model for the sun, how the given the anticyclonic and cyclonic turbulence in the north and south hemisphere. For the northern hemisphere here, we do indeed observe that at least during the solar maximum, and there are sign violations, of course, in the entire solar cycles. In this paper, we have analyzed some 7 years of data. During solar maximum, you do observe that there is a very clear bihelical magnetic field. You see very nice sign separation at some scale. Sunspots dominate the small scale magnetic helicity. Small scale magnetic helicity are essentially contributed by the active regions, and that's where they dominate in essentially the number or the magnitude. But indeed, these bihelical magnetic fields are observed. And that motivated us that we should not impose very strong magnetic fields because dynamo will not give you very strong magnetic fields. And therefore, these are the weak fields imposed in the domain, apart from the usual convection setup. The convection flow looks exactly like this, that you have granules which go bigger and bigger as you go deeper and deeper into the domain. So this is very typical picture also in these simulations or in the simulations of P3s. I don't have to describe here about the criterion. This is all very well known. So this is a typical setup of convection with magnetic field and no rotation in much of the simulations, but we'll also add rotation to test some of the ideas of flux concentrations. And there will be some surprise. So we just run these simulations and observe the vertical magnetic field at the photosphere. And these are the like the usual grayscale plots. You can clearly identify the convection granules here, very much like what you see in observations. And occasionally you do find that there are some even hints of bipolar. These are not like very well formed, but some big spot-like features appearing in the domain. The sizes are typically between 10 to 15 megameter. So at least around 10 to 15 granules. So that is roughly the size, and the strength is around 2 to 3 equipartition field strengths. What we had in the background as little filaments, these are basically weak fields or very small field features. Somehow they come together and accumulate to form an active region. So this process, if you look at the flux emergence, this is one event of a flux emergence, not at the site where the structure is forming, but somewhat away from it. At the site of the structure, there is no indication of any strong upflow or something. A little before that, these arrows indicate some sort of an inflow. I think somewhat like that Matti has alluded to, that little small magnetic elements, they essentially come closer and closer, coagulate and form such somewhat bigger monolith-like structure. Physical mechanism, I would say, is not very well understood. We are still investigating these. Stability of these structures in these simulations is around 20 hours to, in best cases, about say 2 days at most. The emergence as such is a linear in time type process. There is no instability as such in forming these spots if we were to simply collect the fluxes from the neighboring things. So if you just take, define some area element and count how the flux is changing as a function of time, this doesn't show any instability as such. There are, of course, questions, and these are age-old questions that have been asked. What is the mechanism causing these concentrations? What determines their sizes? After all, nature seems to offer variety. If you look at the sun, you find all types of sizes or their lifetime, their scales, everything. Basically, nature does offer variety. And in these simulations, more like what Matthias showed on the Bobstein and Nordlund simulation, these are basically appearing on all types of scales between 5 to 15 megameters with different varying stability. In fact, smaller ones appear to be even more stable. With some characteristics that we are still investigating, but these structures are nevertheless forming. These are strong fields. And the question remains, what is producing these? Is it due to NEMPI? Some of you might already know that there is an interesting idea proposed and very well known, at least in the pencil code community, is a negative effective magnetic pressure instability. And a lot of the co-authors have worked on this. Yes. So I'll also quickly show why we think there is no NEMPI. This is not due to NEMPI. At least we don't find any evidence of NEMPI, despite the effective pressure being negative. And I'll simply highlight that at least we think that the mechanism that might be playing a major role here is the turbulent diamagnetism, which is very close to the idea proposed by Nigel Weiss and Parker in terms of flux expulsion. More technically, I think just the turbulent diamagnetism. There are many such instances of this spot formation, not very clear both poles, but quite often both polarities are shown. The rotation in some of the simulations was non-zero to test whether NMP is working. We nevertheless find the structures. NMP is expected to be suppressed in the presence of rotation, and we rule out NMP. First, because there is no instability, like there is no exponential behavior. Second, structures nevertheless survive the rotation, so doesn't look like NMP, despite the effective pressure is indeed negative. But there is no instability, we think. So these are the ideas that if you have a small scale magnetic, by the way, there is a strong small scale dynamo as well in these simulations. Small scale dynamo is always working given the resolution of these simulations and the Reynolds number being very large, the small scale dynamo cannot be avoided, and NMP seems to be suppressed also by the small scale dynamo. So that might be two different reasons why NMP might not be operative. There are some interesting PDFs. I'll not get into this in the interest of time. We do find, at least by co-aligning and some spatial correlations, that these structures that you see on the top, they are essentially concentrated or seen above a downdraft lane of a deeper layer. And downdraft lane of a deeper layer is basically the depth, width of the downdraft lane is also a function of the depth. And in our opinion, that is what is controlling the size of these spots on the photosphere. You can simply project it out on the photosphere, which will now contain many more venues at the photosphere. And that is what. And these are essentially the flux expulsion. If you average many cells on the photosphere, depending on how many hours you average, you'll find that deeper and deeper layer convection will survive in terms of its appearance. And that cell is essentially, will show you or does show that the flux, magnetic flux is expelled from the regions of upwellings and concentrates more on the regions of downwelling. That's the idea of turbulent diamagnetism, that the magnetic flux will be pumped from regions of a strong turbulent intensity to the regions of lower turbulent intensity. That is from the upwelling to a downdraft. And that seems to be the working mechanism, at least in these simulations. These are early ideas that you know, many of you know, by Parker 1963 and Nigel Weiss 1963. These are the plots from Parker, by the way, that this is the center of the granule, which is say the upwelling, and this is towards the downwelling or the downdrafts, and the magnetic flux as a function of time builds towards the downdraft. If you start from some uniform field, as a function of time, the flux is expelled from the interior region and is concentrated towards the edges of a convective cell. Something like what Nigel Weiss has also explored. The magnetic flux is almost entirely expelled from regions of rapid motion and concentrated at the edges of the convective cells. But these are the convective cells in these simulations of a deeper layer, and therefore the sizes are bigger. Yeah.
15 minutes are over. Can you please?
Yes. So I'm just at the conclusion. Sorry for that. So we do find that the spontaneous flux concentrations are seen in these high resolution simulations. Typical strengths are around 2 to 3 times the equipartition strength. And I think there is no sign or there is no evidence of very strong flows or upflows before there is any flux formation there. So it is exactly consistent with the convective flow speeds, which is also what Matthias has described. Typical sizes are like this. Maximum imposed field strengths are very weak and consistent with what we would expect from an alpha-driven dynamo. Evidence for an alpha effect working in the sun, I've already shown in terms of some observations. Effective pressure is negative, but there does not seem to be any corresponding instability. We think that the turbulent diamagnetism or flux expulsion based ideas could play a very important role in governing not only the formation, but also the size and the time scales of these spots. Thanks.
Thanks, Nishant. Vidya, please.
Yeah, so to confirm that this is due to diamagnetic pumping, did you conclude the...
I can't hear you, Vidya. Can you say again? I couldn't hear you.
So do you hear me?
Yes.
Okay. Yeah. So to check that is it due to diamagnetic pumping, did you compute the turbulent diffusion and then you compute the grad of
Yeah. To some extent, in models like this, it's first of all not very straightforward to simply come up with a definition of eta t. What will you consider as eta t is already a question. But nevertheless, if you take some very simplified URMS by 3KF type idea, that was done, and indeed that does show that eta t is stratified horizontally, and therefore negative grad eta t will point from upwelling to downwelling.
Okay, I got it. Yeah. So I just have a quick question. So if you allow this simulation to run for many days,
which was not possible, yes. Yeah, but yes. Yeah.
Okay, fine. I'm good.
Yeah, which was not possible because of the computing time allocation. These were very expensive runs, and we ran out of our time.
I understand. Okay, good. Thank you.
Yeah, Nishant, you made a point several times, which is that the large-scale dynamos cannot produce fields which are equipartition or over that field strength.
Yeah, we don't see that.
And this is something that has been known traditionally as a problem in
yes. Yeah. Yeah.
So given this scenario, given this, where you're coming from, how do we explain that we still see kilogauss level flux tubes, which require about 50 kilogauss flux tubes, probably emerging, from somewhere at the base of the convection zone?
No, but see these flux concentrations already that I show in these simulations, that are already super equipartition, right? So, and that means they are not coming from dynamo. These flux concentrations, or what you call flux tube, I'm doubtful that they are coming directly from dynamo. Dynamo might give you something sub-equipartition, and you need some secondary mechanisms to boost it further.
But are you sure that sub-equipartition fields which are forming at the base of the convection zone can even coherently rise to have some of the global properties that
in my opinion, I don't see. That's why we have see in this shallow box. I can only speak for this shallow box. I have not seen or have not said that there is anything rising. They are being brought by convection, which is very natural. That convection will bring out some small field elements, but the entire there is some global large-scale field that is rising throughout the convection zone. Something I find it hard to understand or comprehend.
So I would urge you to do a global simulation for the full sun and see if you can reproduce the large-scale observed characteristics like tilts and latitude of emergence of sunspots with just near surface dynamo. I think you will find that even more challenging. So I don't think that is the answer to this.
That's fine, but doing it with convection, doing it with full turbulent magnetoconvection, entire convection zone, as also Mati has highlighted, this will not be very easy. And therefore, we are taking piece by piece. First of all, tilt. I don't know, maybe Hannah will discuss something about tilt. That may be a smaller issue because tilt is acquired apparently post-emergence. And that could just to be do with the helicity of the kinetic.
So maybe we're just looking at a tail and trying to figure out if this is an elephant or a rat. So it could be quite a problem, I think.
Yeah. Okay. We are running out of time. So Sushant, can you just ask very quickly?
Okay. I was just concerned about the energetics in your simulations. If you think everything is like this magnetic field in sunspots is being created and is coalescing at the surface, does the kinetic energy in convection and differential rotation at the surface, is that enough to produce the level of magnetic energy that we see?
See, the magnetic field in concentrating these is not produced or even boosted, in my opinion, by these this thing. Magnetic field you have to produce by some other mechanism like dynamo, and what strengths you get from those is a different question altogether. Here, all I'm saying is that even if you impose a very weak field, and the small scale dynamo is, by the way, already working there, which also saturates nevertheless, not at the super equipartition, but at a sub equipartition. So I have not seen any evidence of a dynamo saturating at very super equipartition level. So that might be my ignorance. But you have, but if you have some secondary mechanisms, NEMP was one possibility, but suppose some other mechanism like flux expulsion, in which little magnetic features are brought together to form these. So that is simply like adding two vectors, right? And that is one way you can enhance the magnetic concentration locally without really disturbing the overall energetics, because you are simply shuffling the fields around and the overall magnetic field is continuously being regenerated by other dynamic mechanisms. So that might not be a problem in my opinion.
Okay, thank you.
Okay, so this is purely advection.
Sushant, sorry, we are running more than 15 minutes late. So we are moving to the very last talk of the session.
Yeah. So our next last speaker is Nitin Yadav. She will from KU Leuven, Belgium, and she will be presenting her contributed talk on slow magnetoacoustic wave propagation in 3D simulations of a unipolar solar plage. Nitin, you may go ahead. I will 12 minutes.
Okay, thank you. Yeah, I'm Nitin. I'm a postdoc at Center for Mathematical Plasma Astrophysics at KU Leuven. And first of all, I would like to thank the organizers for giving me this opportunity to present my work here. And I will be talking about slow magnetoacoustic wave propagation in 3D simulations of a unipolar solar plage region. And I did this work at Max Planck Institute for Solar System Research in collaboration with Robert Cameron and Sami Solanki. 1 minute. Yeah, so let's start with a brief background. So MST waves are of great interest in solar physics because of two major applications, namely magnetoseismology, in which these waves can provide information about the solar atmosphere through which they are propagating. And secondly, for their role in solar atmospheric heating, because they are capable of transporting energy from the lower layers to the higher layers, where they can eventually get damped and dissipated and heat the surrounding plasma. And moreover, they are also suggested to be associated with various observation phenomena such as solar specules. And so for a long time, the studies related to MST waves were mainly theoretical. But in the last 3-4 decades, with the advent of spectroscopic and imaging instruments, it became possible to observe them or to detect them through direct observations. And in the last 2 decades or so, in the direction of theoretical modeling using MST simulations, it was possible to investigate the propagation through the atmosphere using some velocity drivers at the bottom boundary with the parameters that are directly or which are compatible with the direct solar observations. And now with radiation MST simulation or the so-called realistic simulations, we can actually study propagation or these MST waves in a more natural way, because we need not use any external velocity drivers, and these waves are naturally excited because of the turbulent convection and other processes in the convection zone, and then we can study their propagation into the higher layers. As Ragnar has already mentioned about this in detail in his talk today, so thanks for that. So, my motivation for this work was to investigate MST waves, in particular slow magnetoacoustic wave that are excited naturally due to the turbulent convection. And I will be using high resolution, high cadence realistic MST simulations for this study. So this slide displays describes the simulation setup that I have used. So I have used Muram code for simulating a unipolar solar plage region. And the dimension of my simulation box is 12 megameter by 12 megameter in the horizontal space and 4 megameter in vertical direction, which is such that it is 2.5 megameter above the surface and 1.5 megameter below the surface. And the spatial grid spacing in all the 3 directions was 10 kilometers. And I initiated the simulations for a hydrodynamic case, and then later on introduced a vertical magnetic field of 200 Gauss, and then evolved it again so that the system reaches a quasi-steady state. And then we started collecting the data. And since the aim was to study magnetoacoustic waves or the MST waves, so we wanted to save at a high cadence or the high temporal spacing. So we saved the data for 25 minutes at 1 second cadence. And since it was a very high resolution data, so we didn't want it to compromise on the spatial resolution. So we selected a smaller sub-region for this wave investigation. So we selected a region of 3 by 3 by 3 megameter cube for the wave investigations. So the figure here displays the 2D map of the vertical component of magnetic field strength at mean solar surface. And this is the saturated map between plus minus 100 Gauss. And so we can see there are some strong magnetic concentrations which has magnetic field strength of kilogauss level, and there are some mixed polarity region also formed. Now for this wave investigation, we selected a smaller subregion which corresponds to this red color square here, and also zoomed in the right panel now. And now since we want to study waves which will be propagating along the magnetic field lines, so we wanted to trace and to follow the individual magnetic field lines so that we can correctly apprehend their wave properties. So we place some seed points in the center of the selected domain, which are shown here by these 25 asterisks. And now let's see how do we track these individual field lines. So this cartoon here demonstrates the procedure that I have used for tracking these magnetic field lines. So let us assume that at time equal to 0 at the beginning of the time series, we have a fluid parcel or a seed point at the location A at mean solar surface. And then we have the magnetic field vector data for that time snapshot. So we use the magnetic field vector information and trace the magnetic field line in 3D space. And then we use the velocity vector information to see how much this fluid parcel will be displaced in 1 second. And for that, we integrate the location in time, assuming that the velocity does not change much in that course of 1 second, which is quite a valid assumption because velocity in 1 second doesn't change much. So suppose we move to a next location B in 1 second, which need not necessarily be on the mean solar surface. It can be above or it can be below. Then again, using the magnetic field information at that time snapshot, we trace the magnetic field again. And then we come back to the mean solar surface for the next time snapshot. So we continue doing this procedure for 25 minutes. And that way we follow the magnetic field line, which was initially associated with our seed point A. So I did it for all the 25 locations that I have shown earlier. And for one example case, I'm showing here. So we are interested in this problem on the slow magnetoacoustic waves, in which we know that the velocity oscillations are longitudinal. So we compute the velocity components along the magnetic field line and while tracing the magnetic field line in both space and time, and then constructed a space-time map, which is shown here. So the background map shows the propagation of longitudinal velocity along the magnetic field line with time. So we can see there is a forward propagation of these perturbations along the field line, and the overplotted black line shows the path line for the test particles, which will be moving with the local sound speed. So we can clearly see that up till and height of 1 megameter, they are propagating linearly with the local sound speed. But after that, these slow magnetoacoustic waves are converting into shock because of the sharp density decrease in the chromosphere, and they are moving faster than the local sound speed. So this was when we are following the single magnetic field line in both space and in time. But in observations, we know it is not possible to follow the magnetic field line as we can do in the simulations. So we'll be looking at a fixed point. So let us assume that we are having observation of 10 kilometer resolution and we are looking at one fixed point, then how this map will look like. So this is what we get if we are not moving with the field line and looking at a fixed position. So you can see that now the map we are getting is not at all smooth, and there are various intermittent fluctuations, and it's not smooth at all like when we were following the field line. And the reason for this is that within a single magnetic element itself, the neighboring field lines are not in phase. So when we are looking at the fixed position, there are many field lines coming and going from that fixed location. So we are getting these intermittent fluctuations. So therefore, it tells the importance of tracing a field line in space and in time so that we can correctly infer the wave properties. Now to calculate the dominating wave period, I calculated wavelet power spectra at different heights for all these 25 seed locations and calculated an average. So these 4 panels display the average power spectra over these selected seed points for different heights. So near the surface at z equal to 0, let's say, the dominating wave period is around 6 minutes. And as we go to higher layers, it shifts to smaller wave periods or to the higher frequency, which is because the solar atmosphere poses a acoustic cutoff and cutoff frequency, and it doesn't allow to lower frequency waves to propagate through it. But I would like to emphasize here that this average is a biased average because we are averaging only on the 25 locations which are associated with mostly vertical magnetic field lines. So to get an overall picture of the whole Plage region, we calculated the power spectra for the complete horizontally averaged domain. So this is the power spectra that is averaged over the whole horizontal domain. And I will explain these panels. So these 4 panels are for different heights, and heights are mentioned on these panels itself. And these colors, like the black curve, is for when we are calculating the velocity power spectra using the longitudinal component of velocity, because that is the one which will be associated with slow magnetoacoustic wave. And the red color corresponds to the velocity power spectra calculated using the vertical component of velocity vector, because in observation, it is not possible to calculate the longitudinal component always. We'll be looking at line of sight, which will be mostly vertical. So the red curve corresponds to the vertical component of of the velocity vector. And again, these simulations were with the spatial grid spacing of 10 kilometers, which is still very far from the observations. Therefore, we degraded our simulation data with the Gaussian kernel of 100 kilometer full width half maximum, and also with 200 kilometer full width half maximum. And the blue color is for 100 kilometers, and the green color curve is for the 200 kilometers. Now here, let's first focus on the dominating wave frequency. So near the surface, we have the dominating wave frequency around 6 minutes, 5 to 6 minutes, which corresponds to 3 millihertz. And as we are going higher in the atmosphere, for example, in 500 kilometer here and in 1000 kilometer and 1.5 megameter above surface, we can see that the dominating frequency is shifting to the high frequencies, which is again due to the cutoff. But the interesting thing here is that even in the higher layers, the velocity power in the lower frequencies, which is associated with the 5-minute oscillations, is not negligible. For example, if you focus on 500 kilometers and in 1 megameter, we can see that there is still a significant amount of power, which corresponds to the 5-minute oscillation, which is still able to leak from the lower layers to the higher layers. And this is a special characteristics of Plage region that has been reported widely in the previous observations, that it is different from the sunspot in a way that these low frequency waves of the 5 minutes oscillation are still able to propagate to the higher layers. And again, another point that I would like to draw your attention to is that with the spatial degradation, yes, we are losing power, which is expected because we are averaging over the spatial domain. But this drop in the power is more affecting the higher frequency waves, as you can see on the right part of these panels, than the low frequency waves. And which is due to the low frequency waves are actually associated with the large spatial sizes. So they are not much affected by the spatial averaging, but these high frequency waves, they are associated with small spatial scales. So they are more influenced by the spatial averaging.
I think 12 minutes are done. Can you?
Yeah, sure, perfect. Yeah, thank you. So next, we wanted to calculate what is the energy contribution, or what is their role in the energy balance in the Plage region. So to calculate that, we calculated the acoustic flux in our case, which is calculated using this formula that is shown here, which makes use of averaging of velocity power spectra. So in this case, we are averaging over 2 to 500 millihertz. This lower limit is set by the observation, which report, for example, by Centeno et al. In 2009, which report that the cutoff frequency for the Plage chromosphere is posed around 2 millihertz. So all the waves which are having frequency more than 2 millihertz will be able to propagate. And the upper limit comes from the Nyquist frequency, because we have cadence of 1 second, so we can go up to that frequency range. Again, the color coding is the same. So we can see that by measuring the longitudinal component, and instead of calculating the vertical component, we are gaining a factor of around 2. And again, with the spatial degradation going from 10 kilometer to 200 kilometer, we are again losing a factor of 4 in the total wave energy flux. And the values that we are getting here are compatible with they are able to compensate for the radiative losses in these layers. And I have shown only up till 800 kilometers above the surface for 2 reasons. One is the top boundary is close, so it can affect the higher layers. So we don't trust the results in higher layers that much. And also the relationship that I'm using to calculate the acoustic flux is valid only for the domain where the waves are propagating linearly. And as I have shown earlier, above this height, waves are converting into shocks and they are no longer linear in nature. So we cannot use this relationship to calculate acoustic flux at higher layers. So this brings me to the conclusion for my work. So we found that magnetic field lines are carrying slow magnetoacoustic waves and they are continuously advected by the plasma flows in the photosphere. Therefore, it is important to follow the track the magnetic field lines to get their correct parameters. And the power spectra of the longitudinal velocity averaged over the selected field lines show that the periodicity or the frequency, dominating frequency of the oscillations that shift from the higher frequency, that shifts from lower to the higher frequency in the chromosphere, and which is also consistent with the previous observations. And however, the horizontally average power spectra show that there is still a significant fraction of low frequency waves that can leak from the lower layers to the higher layers. And yeah, that is also consistent with the previous observation. And that is mostly, or we think it is most probably because of the inclined magnetic field lines. And we also find that the poor resolution, for example, 100, 200 kilometers, or as well as not observing the longitudinal component and calculating with the vertical component, vertical component can lead to an underestimation of wave energy flux by up to a factor of 4 in the upper photosphere and in the lower chromosphere. And the acoustic wave energy flux for the slow magnetoacoustic wave from our calculation is sufficient to account for the radiative losses in plage. Yeah. So thank you for your attention. And yeah, I will be happy to take any questions.
Thanks, Nitin. Somebody from IIA?
Hi, so this is Rajaguru from the IIA auditorium. So it was an interesting talk. Your plot showing the velocity power for different heights. There are 4 panels here. So for the lowest height, you see the largest difference between vertical and the longitudinal component. Is that, do you understand why?
Yes, because near the surface, magnetic field is expanding. So there the curvature is more. So there we get a difference between the vertical component and the line of sight component. But in higher heights, it is mostly vertical. So it doesn't make much difference whether we are measuring the longitudinal component or we are measuring the vertical component. So in higher layers, we don't see much difference. And in around 1500 and 1000, there's not really a significant difference in the red and black color. You cannot even differentiate them. Yeah, but in lower layers, yeah, because of the expansion and the inclination of the magnetic field line, it makes a difference.
So that means if you go further down, close to the photosphere, again, they should the difference should decrease.
Yes. No. Sorry?
If you go further down, here
yes.
It is vertical, so it should again decrease.
Yes, yeah. So it is mostly because of the inclination of the magnetic field in the photosphere, yes.
Okay, thank you.
Durgesh, please.
Hi, Nitin. Thanks for the nice talk. So I have one rather naive question. You mentioned this Withrow and noise calculation done in 1977. So are there any updates or any correction to that value, or are we still carrying that values from 70, and how accurate is that value is then?
Yeah, there has been a very recent study in last year, I think in 2020, which are predicting that these numbers are on a very lower level, and actually the required energy flux is much higher. But I still compared it with the previous work because that is like well known, and yeah. But there has been a recent study. I haven't compared my results with that work, but yeah, there is a new estimation of required energy flux.
Okay, thank you.
Pankaj?
Yeah, thanks, Nitin. Nice talk. My question is in terms of damping. So I have an impression that your high frequency, waves are damped more efficiently than the low frequency. So probably that's also a reason why the low frequency components are traveling to much higher heights. Of course, you are limited up to chromosphere. Still, you are not seeing the transition region. So my question would be, have you looked at the damping component of it, and what's the next plan? I mean, would you include the transition region and see the effect of the transition region on this?
No, for my, like I plan to investigate other waves first, like the transverse waves next, using the same simulation instead of doing a new simulation with including transition region and above layers. Yeah, for damping, yeah, because high frequency waves are actually associated with smaller spatial scales. So they are more prone to damping and dissipating. Yeah, so that's why they are not able to propagate much higher, I would say. Yeah.
You know, in a wavelet plot also, there is an indication because, you know, one needs to look at this, yes. So one needs to look at, you know, not the global one, but the one in the left panel. And there you do have a signature of the damping as well. So I was wondering whether you have tried to do any statistical work on looking at different locations and seeing, you know, which one is more efficient and things like that.
I have done one investigation that I can share. Maybe that will be relevant here. So I did this phase coherence study. Sorry, not phase coherence, but the coherence study between the for different frequency ranges. So so these 4 rows are for different heights, and 3 columns are for different frequency ranges. So the left one is for the frequency range between 2 to 5 millihertz, which is for the low frequency, and the extreme right is for high frequency between 20 to 25 millihertz. And now if we look at the phase, so we can see that the low frequency wave are much more in phase with the neighboring field points, whereas the high frequency wave is not at all in phase with the neighboring field points.
Yeah.
So so that's, yeah.
Yeah, observationally, we do see the exact things even very high in the atmosphere. So that's why I was saying that really the transition region is probably not making the things change much. Exactly same feature we are seeing in the higher up as well.
Okay, yeah, that's good to know. Hello?
Yes, hi Nitin. Thanks for the very nice talk. So just a question for the power spectra that you showed. I mean, you said, I mean, it's a horizontally average, right? So what is the range of the inclination angle? Because inclination angle could potentially, I mean, it changes, I mean, the cutoff frequency. And if you average over a very large range of inclination angles, it could actually influence, I mean, it's the power spectra that you show.
Yeah, so these, sorry. So these power spectra are averaged for 3 megameter by 3 megameter range. And yeah, for the inclination, I couldn't calculate, I didn't calculate actually how much angle they are, like what is the distribution of the inclination angle, but yeah, I don't know how much they are spreading out.
Okay, it's interesting actually to see the effect of that because inclination angle, as you know, I mean, changes the cutoff frequency. So then it could be interesting to see, I mean, if you're averaging over a very large range of inclination or it's not, I mean, or how the effect is. I mean, it can be very interesting.
That will be an interesting point to check. Yeah, I can. Yeah,
Thank you very much. Thank you. Thanks.
Okay, thank you.
Thanks.
With that, we are going to finish this session. So Sampurna, you want to?
Yeah, thank you all the speakers for a very interesting talk and all the participants for interesting discussions. Maybe they can be continued in the Slack channel. So we close this session and it's over to the organizer.
Okay, so thank you everyone, especially the speakers who were in a kind of strange time zones. Matthias for a late night presentation and probably Nitin was from very early morning. Thank you all for this wonderful talks today. So we have a break, lunch break now for an hour and a half. Yeah, so we will meet at 2 p.m. Indian Standard Time again for the next session on computational solar physics. Okay, so we will close the Zoom meeting now. We will open it 15 minutes before 2 o'clock. Okay, see you all in about an hour. Thank you.